What kind of world invents eyes, armour, and hunger almost at the same time, 541 million years ago? Earth's oceans began to change from quiet microbial floors into crowded alien gardens, filled with trilobites, spiny little survivors, burrowing shadows, five-eyed hunters, and the great strange silhouette of Anomalocaris moving through the water. This is the Cambrian Explosion, when life did not simply become more complex, but suddenly became watchful, armoured, beautiful, and dangerous. If this deep-time journey helps bring calm wonder to your day, please leave a like, subscribe for more slow science stories, and share it with someone who loves Earth's ancient mysteries. Thank you for spending your time here, and as the video begins, feel free to comment what time it is where you are, and where in the world you're watching or listening from. Now, let the ancient sea open. Long before the sea filled with armoured bodies and restless hunters, Earth carries a quieter world through the last age of the Proterozoic. The continents are arranged differently from the maps of the present, scattered across an oceanic planet under a sky with less oxygen than modern air and a moon that still appears slightly larger from the surface. The land is bare rock, mineral crust, wind, and water. No forests soften the slopes, no insects cross the mud, no roots hold the shorelines together. Life belongs mostly to the sea, and even there it remains gentle in outline, dominated by microbial mats, drifting cells, sponges in their early simplicity, and soft animals pressed close to the seafloor. This is the late Ediacaran world, a time when complex life has begun to become visible, but not yet forceful. It does not yet rule its surroundings with teeth, shells, claws, or speed. It lies, fronds, spreads, ripples, filters, absorbs, and waits. Many of its shapes seem almost like experiments in being alive, broad quilted bodies, leaf-like forms anchored in the current, oval impressions left in sediment, and slow traces across ancient surfaces. They are not primitive in the sense of being unfinished. They are suited to a planet that has not yet become crowded with animal conflict. They belong to a slower grammar of survival, where the most important forces are chemistry, light, oxygen, water movement, and the steady skin of microbes covering the sea floor. But beneath this softness, the planet is unstable. The Ediacaran follows some of the coldest intervals Earth has ever known. Earlier in the Proterozoic, vast glaciations may have pushed ice toward the tropics, locking much of the surface into a reflective white shell. These snowball Earth episodes remain among the most severe environmental trials in the planet's record. Their exact reach and rhythm are still debated, but their influence is difficult to ignore. When ice spreads across the world, shallow habitats shrink, sunlight changes, ocean circulation slows, and life is pushed into refuges where chemistry and temperature remain tolerable. When the ice retreats, the ocean does not simply return to what it was before. Weathering intensifies, nutrients wash from exposed rock, carbon moves between air, ocean, and stone. Oxygen may rise and fall in pulses. The living world is forced through a narrow passage, and what emerges carries the memory of selection, hardship, and opportunity. Near the end of the Ediacaran, the record hints at another cold interval, sometimes associated with the Gasquia's glaciation, and with later regional evidence for renewed climatic stress. It is not certain that this event froze the planet in the same overwhelming way as earlier glaciations, and many details remain unsettled. Yet even a more limited glaciation could have mattered deeply to shallow marine life. The animals of this time have little protection against rapid environmental change. Many live close to the sediment surface. Many depend on stable microbial mats, predictable oxygen, and water conditions that do not swing too violently. a colder world, followed by thawing seas and altered chemistry, would place pressure on these quiet communities. Some forms vanish from the record, others persist for a while. Some may leave descendants, though the relationships are often uncertain. The fossils do not speak in clean lines of ancestry. They appear as impressions, surfaces, sudden absences, and rare moments when soft tissue meets conditions gentle enough to preserve it. Because of that, the end of the Ediacaran is not a simple curtain falling. It is more like a shoreline at dusk, where familiar shapes fade gradually and new movement begins in the dimness. The soft-bodied organisms that live through this time are often described by what they lack. They do not have hard skeletons. They do not have obvious heads. They do not show the same organs and limbs that make later animals easier to understand. But absence can be misleading. Their world has its own complexity. Microbial mats stabilize sediment and create layered landscapes across the sea floor. Organisms feed by absorbing nutrients, filtering water, grazing films, or disturbing the sediment in small ways. Some leave trails that suggest controlled movement. Some occupy the water column. Others attach themselves like living banners in the current. The environment is not empty. It is only quiet by the standards of what will come later. In this quiet, the first hints of future change begin to gather. Burrows become more important. Sediment that once remained neatly layered by microbial mats is increasingly disturbed by animals moving through it. This behavior is known as bioturbation, the mixing of sediment by living organisms in a calm scientific sense. It is one of the most important revolutions in Earth history. A creature that burrows does more than hide. It opens pathways for oxygen. It changes how nutrients are buried and released. It breaks the stable surface that mat-based organisms depend on. It turns the seafloor from a sealed skin into a living, shifting boundary. At first, these traces may be simple, shallow, and sparse. But they show that some animals are no longer only resting on the world. They are entering it. They are making the sediment into habitat. This matters because the future Cambrian seas will not be built only from new bodies. They will be built from new behaviours. The planet itself is also changing in ways that favour a more active animal life. Oxygen remains a central part of the story. Larger bodies, faster movement, and tissues with high energy demands all require more reliable access to oxygen. The exact timing of oxygen increases is still debated, and it would be too simple to say that one rise in oxygen caused the Cambrian explosion by itself. But oxygen is part of the foundation. It sets limits on what bodies can do. When those limits loosen, evolution can explore forms that were previously difficult to sustain. Nutrients are another part of the foundation. As glaciers grind rock and expose fresh minerals, and as weathering carries elements into the sea, the base of the food web can become more productive. More microbial and algal growth can support more animals. More animals can support more ecological relationships. A world with more energy moving through it can become a world with more roles to fill. Yet none of these changes acts alone. Climate, oxygen, nutrients, genetics, development, and ecological interaction overlap like slow currents. The Cambrian explosion is not a single spark. It is a threshold crossed by many processes at once. The late Ediacaran communities stand directly before that threshold. They are beautiful partly because they are difficult to place. Some may be early animals. Some may represent branches of life with no close modern equivalent. Some may belong near groups that later flourish, while others may be evolutionary side paths that end before the Cambrian world fully arrives. Their strangeness is not the same as failure. For millions of years, they belong to their planet. They occupy real ecosystems, respond to currents, settle on sea floors, and become part of the long preparation for animal complexity. But as conditions shift, their advantages weaken. A broad, soft body can collect nutrients in a mat-covered world. It may not fare as well when sediments are churned, when oxygen gradients change, when new animals move more actively, or when feeding becomes more direct and competitive. A sea floor once covered by microbial carpets becomes more broken, more penetrated, more unpredictable. The older Ediacaran style of life does not disappear in a single instant, but it begins to lose the calm ecological stage that made it possible. In that loss, there is no drama in the human sense. There is no intention, no warning, no sudden announcement from the rocks. There is only the patient pressure of a planet-changing state. Ice advances or retreats. Shorelines migrate. Sediment hardens, erodes, and is buried. Oxygen enters water at one depth and vanishes at another. Small animals probe downward. Microbial mats tear and reform. Generations pass in numbers beyond easy imagination. The fossil record preserves only a thin scattering of these lives, yet the pattern is clear enough to feel the approach of something immense. By the beginning of the Cambrian, around 541 million years ago, the ocean is no longer merely a refuge for soft experiments. It is becoming a stage for speed, armour, vision, pursuit, and defence. The world at the end of the Ediacaran is therefore not just an ending. It is the frozen threshold before a new ecological language. The old sea is still dim, still quiet, still filled with forms that seem to hover between categories. But beneath it, the rules are loosening, the sediment is opening, the water is changing. The surviving lineages are carrying their small advantages forward, somewhere in those shallow seas, among mats and burrows and fading soft-body communities. Life is preparing to become strange in a different way. Not only soft and mysterious, but mobile, watchful, armoured and hungry. After the late Ediacaran world passes through its unsettled threshold, the beginning of the Cambrian does not arrive as a clean sunrise over a new planet. It arrives through recovery, through shallow seas changing their chemistry, through shorelines shifting over continental shelves, and through living communities rearranging themselves around absences. Empty niches are not truly empty in a physical sense. They are spaces of possibility inside an ecosystem, ways of living that are not yet fully occupied or are newly available after disturbance. A niche can be a place, such as the surface of a microbial mat, a burrow beneath the sediment, or the water just above a sponge community. It can also be a role, such as scraping films from the seafloor, filtering suspended particles, hiding inside mud, swimming after small prey, or breaking down organic matter before it disappears into the sediment. When climate stress, oxygen shifts, sea level movement, and ecological turnover unsettle older communities, some of these roles become open. The animals that remain do not inherit a quiet paradise. They inherit a world with room to try new solutions. In the wake of Ediacaran disruption, that room becomes one of the deepest forces in the history of life. The Cambrian seas spread across broad continental margins, where sunlight reaches warm, shallow water and nutrients collect in productive layers. These shelves are not uniform blue plains. They are mosaics of mud, sand, carbonate flats, microbial surfaces, sponge grounds, low slopes, oxygenated shallows, darker basins, storm-washed bottoms, and protected lagoons. Each difference creates a slightly different challenge. A body that succeeds on a firm microbial surface may not succeed in loose sediment. A feeder adapted to suspended particles may not prosper where food settles in films. A soft animal resting in the open may thrive in one setting and become exposed in another. The more varied the seafloor becomes, the more varied life can become in response. This is one reason recovery after environmental stress can lead to expansion rather than simple return. In this early Cambrian interval, the living world begins to occupy those gradients with a new intensity. Animals move across the surface, into the sediment, and through the water above it. Some continue older ways of life, feeding passively or slowly on microbial growth. Others begin to exploit food more actively. The difference may seem small at first, but in evolution, a small behavioral change can open an entire landscape. A creature that can crawl farther can find food others miss. A creature that can dig deeper can escape disturbance or reach buried nutrients. A creature that can sense light and shadow can orient itself more safely. A creature that can harden a small part of its body can resist damage, anchor more firmly or scrape with greater force. None of these changes needs to appear fully formed. Natural selection works with slight differences repeated across generations. Over time, small gains become habits of body plan. The Cambrian Explosion is often described as sudden because it appears abrupt in the rock record, but the word sudden can be misleading. In human terms, the transformation still unfolds across millions of years. The deeper point is not that animals appear from nowhere. It is that many lineages begin leaving clearer fossils, more complex traces, and a wider range of mineralized parts within a relatively compressed interval. Shells, spines, plates, burrows, tracks, and body impressions begin to write animal life into stone with greater detail. Hard parts fossilize more easily than soft tissue, so the rise of mineralized structures makes Cambrian life more visible. But visibility alone does not explain the pattern. The ecosystems themselves are becoming more complex. The number of interactions is increasing. Animals are not just present, they are beginning to influence one another in ways that reshape their future. Open niches help explain why diversification can accelerate. When many roles are available, a lineage does not have to compete only by replacing another form directly. It can move into a slightly different way of living. One branch may specialize in feeding near the sediment surface. Another may become better at swimming. Another may protect itself with armor. Another may flatten its body and hug the bottom. Another may elongate and slip through mud. In this way, ecological space becomes a branching structure. Each new adaptation can create further openings. Burrowing animals alter the sediment and make new chemical layers. Grazers change microbial mats and encourage different surfaces. Suspension feeders remove particles from water and change the flow of nutrients. Predators, even early and limited ones, make hiding, sensing, and defense more valuable. The niche is not only discovered by life, it is also made by life. Biology begins to engineer the seafloor with increasing force. The older microbial world does not vanish, but it loses its monopoly over the texture of marine habitats. A mat that once covered sediment like a quiet film is now cut by trails, pierced by burrows, grazed by small mouths, and interrupted by the movements of bodies. This produces a more irregular world, less stable in some ways, but far more open to animals that can use disturbance. For a soft ediacaran organism adapted to a broad mat surface, this may have been a loss. For a small mobile animal able to probe, dig, or cling, it may have been an invitation. The same environmental change can be a crisis for one form and an opportunity for another. Evolution has no single emotional meaning. It is only consequence, carried through bodies. As the Cambrian begins, those consequences multiply. The survivors of earlier worlds carry genetic toolkits that allow bodies to be arranged in segments, fronts and backs, upper and lower surfaces, guts, muscles, nerves, and sensory regions. These developmental systems did not appear fully assembled at the first Cambrian dawn, but by this time they are capable of producing a remarkable variety of shapes. When ecological opportunity meets developmental flexibility, diversification can move quickly, segments can become limbs, shields, gills, or repeated supports. A simple hard part can become a shell, spine, tooth-like element, or protective plate. A nervous system concentrated toward the front can support more directed movement. A gut running through the body allows continuous feeding and processing. These are not merely anatomical details. They are ways of entering niches that older forms could not easily occupy. The Cambrian world is therefore not only a world after hardship. It is a world in which the architecture of animals becomes more adjustable and more ecologically expressive. Still, the opening niches are not an unlimited promise. The early Cambrian sea remains physically demanding. Oxygen can vary sharply between shallow and deeper waters. Storms can bury communities beneath sediment or expose them to erosion. Sea levels rise and fall across continental shelves. Chemistry changes from basin to basin. A small animal may flourish in one local setting and disappear in another. Fossil deposits preserve this patchiness. Some sites reveal crowded assemblages of shelly fragments. Others preserve soft-bodied animals in exceptional detail, as though a brief window has opened into an otherwise hidden sea. Together, these deposits show not a single uniform explosion, but a broad pattern of experiments playing out across many habitats. Different groups rise at different times, and many strange forms never become long-lasting dynasties. The early Cambrian is generous with possibility, but it is also selective. Most possibilities end. This gives the beginning of the Cambrian its particular beauty. It is not only the beauty of success, it is the beauty of trying. A small shell appears and becomes part of a defensive strategy. A worm-like body digs and changes the chemistry around it. A tiny swimmer moves through the water column and avoids the bottom. A mat grazer leaves a delicate trace that will outlast its body by 500 million years. In the immediate moment, none of these lives knows that a new era is beginning. There is no boundary line in the water. There is only feeding, moving, resting, escaping, reproducing, and dying. Yet across countless generations, these ordinary acts become extraordinary. The niches left open by disruption are gradually filled, then subdivided, then transformed into new niches by the very animals that occupy them. The early Cambrian sea becomes not a blank canvas, but a living conversation between environment and anatomy. Every movement changes the conditions for the next movement. Every defense invites a new form of pressure. Every new food source draws a body toward it. Out of this slow exchange, the quiet recovery after the Ediacaran begins to deepen into something far more dynamic. Life is no longer simply returning from a difficult age. It is expanding into the openings that difficulty has made. The stage is not yet dominated by the great names of Cambrian strangeness, not yet by the large radiodont hunters or the most famous armoured fossils. First comes the widening of possibility itself, the making of ecological room. In that room, the small survivors of the ancient sea begin to diverge. Some settle into protection, some test movement, some enter the sediment, some lift into the water. The ocean grows more layered, more restless, and more responsive. Before the arms race can fully begin, before vision sharpens and predation becomes the defining pressure, the Cambrian must first become spacious. It must become a sea filled with vacancies, edges, shelters, food, and risk. In those open niches, life finds the permission to become more various than it has ever been before. The first great change in the Cambrian sea is not the invention of a single weapon, or the sudden appearance of one monstrous hunter, but a quieter transformation in relationship. For most of the visible history of animal life before this point, feeding seems to have been largely indirect, slow, or passive. Organisms filtered particles from water, absorbed nutrients across broad surfaces, grazed microbial films, or disturbed the sediment in search of organic matter. There were pressures, of course. There was competition for space, light, oxygen, surfaces, and food. There were storms, burial events, chemical changes, and climate stress. But the sea had not yet become a place where animal bodies were widely shaped by the need to catch, resist, escape, and outmaneuver other animal bodies. At the opening of the Cambrian, that older balance begins to change. Some animals start to feed more directly on other animals, and with that shift, evolution acquires urgency. A predator does not need to be large to change the world around it. It only needs to make another organism safer by being harder to reach, harder to bite, harder to detect, harder to digest, or faster to leave. Once that pressure appears, even in small forms, it spreads through the logic of survival. A soft body lying on the sediment becomes vulnerable. A slow animal without protection becomes a food source. A creature unable to sense disturbance becomes easy to surprise. Predation creates a moving target for evolution, because every improvement in the hunter changes the conditions for the hunted, and every improvement in the hunted changes the possibilities for the hunter. This is often called an evolutionary arms race, but the phrase should be handled gently. There is no plan, no rivalry in the human sense, no conscious contest beneath the Cambrian water. There are only differences in survival, repeated over generations until bodies carry the marks of pursuit. The earliest predatory pressures may have taken many forms. Some animals may have scraped, rasped, punctured, or swallowed soft prey. Others may have consumed larvae, eggs, or tiny animals hidden among microbial textures. Some may have scavenged dead bodies and then shifted gradually toward living prey. The fossil record rarely preserves behavior with perfect clarity, especially when the bodies involved are small and soft. Yet the evidence appears in patterns that are difficult to ignore. There are damaged shells in later early animal communities. There are defensive spines, plates, and tubes. There is the spread of hard, mineralized coverings. There are more complex traces in sediment, suggesting animals moving with greater purpose, depth, and urgency. There are eyes and sensory structures appearing in groups that must now gather information quickly. The sea is learning a new grammar, written not only in bodies but in reactions. The first pursuit changes both sides of every encounter. For prey, the most immediate answer is protection. A mineralized shell, even a small one, can make the difference between being swallowed and surviving long enough to reproduce. The early Cambrian small shelly fossils are fragmentary and sometimes difficult to assign to modern groups, but their existence speaks to a broad turn toward hard parts. Some are caps, cones, plates, tubes, spines, or tiny armor elements. They may serve different purposes in different animals, but many fit a world in which soft tissue is increasingly exposed to danger. Mineralization is expensive. It requires chemistry, energy, and developmental control. A body does not carry armor without cost. Heavy coverings can slow movement. They require materials from seawater. They may make growth more complicated. The fact that hard parts become widespread suggests that the benefits often outweigh the burdens. In a sea with active consumers, even partial protection can be enough to shift the odds. Defense is not only armor, it is also behavior. Burrowing becomes a kind of refuge, a way to enter the sediment and leave the open surface behind. A shallow tunnel can protect an animal from some predators while allowing access to buried organic matter. A deeper trace may offer more stable conditions, though it also brings challenges of oxygen and movement. The Cambrian substrate revolution, the transformation of seafloor sediment by animal activity, is partly a story of feeding and partly a story of safety. To burrow is to make a shelter from the planet itself. The sediment becomes more than ground. It becomes architecture. Predation may also encourage animals to become less predictable. Instead of resting where food is abundant but danger is high, they move, pause, hide, and emerge. Instead of spreading flat against a microbial surface, they narrow, coil, dig, or lift themselves on appendages. These are small behavioral shifts, but they make ecosystems more dynamic. A world of passive feeding can be spatially rich, but a world of pursuit becomes temporally rich as well. Timing matters, speed matters, direction matters. For predators, the new challenge is equally demanding. To eat another animal, a body must locate, approach, capture, process, and digest prey that may be moving or defended. This favours sensory systems, muscles, grasping structures, mouth parts, and digestive arrangements that can handle more concentrated food. Animal tissue is rich in energy compared with diffuse food sources, but it is not freely available. It must be won. Early predators may have been clumsy by later standards, yet even clumsy predation can transform an ecosystem. A small hunter probing the mud for worms alters the value of deeper burrows. A swimming predator with simple eyes alters the value of camouflage and rapid escape. A grazer that damages soft surfaces alters the value of spines, secretions, or tough outer layers. Each relationship is local and ordinary. Yet the accumulation becomes planetary in scale. The Cambrian explosion cannot be reduced to predation alone, but predation gives the explosion a distinctive shape. It turns diversity into interaction. It makes the body of one animal part of the environment of another. In earlier ecosystems, physical conditions may have been the strongest visible sculptors of form. In the Cambrian, biology itself becomes a more powerful sculptor. Life begins to apply pressure to life with new intensity. This shift helps explain why so many different solutions appear in a relatively short geological interval. Some lineages respond by becoming harder, others become faster, others become smaller, more flexible, or better hidden. Some evolve repeated limbs or plates. Some develop sensory regions at the front of the body, because the front is where a moving animal meets the world first. Some invest in swimming. Some cling to the bottom. Some remain nearly motionless but become unpleasant or difficult to eat. The sea becomes an arena of strategies, though still a quiet one when seen from the scale of deep time. No dramatic boundary separates before from after. There is only the increasing complexity of consequences. The rise of predation also changes death. In the Cambrian, more bodies are torn, bitten, swallowed, fragmented, and recycled through other bodies. Nutrients move differently when animals consume animals. Energy passes into more concentrated channels. Waste, shells, molts, and broken remains accumulate. Molting arthropods shed outer coverings. Shelly creatures leave durable fragments. Scavengers exploit what predators leave behind. This recycling does not simply end lives, it builds ecosystems. A damaged body becomes food for another organism, then waste for microbes, then chemistry and sediment. Predation tightens the loops between animal life and the material planet. It also raises the importance of reproduction and early life stages. Larvae, eggs, and juveniles may be especially vulnerable. In response, life histories can shift. Producing many offspring, dispersing larvae through the water, or protecting early development can all become valuable in different contexts. Once animals eat animals, every stage of life becomes part of a food web. There is a deep calm in recognizing that this great turn toward pursuit was made from countless modest moments. A tiny animal avoiding a shadow, a soft-bodied creature sinking beneath the surface, a small predator testing the sediment with appendages, a shell thickening over many generations, a sensory patch becoming more useful because danger now has direction. These are not spectacular events in isolation. They are the ordinary mechanics of survival. Yet together they create the beginning of a world that feels more familiar than the Ediacaran, even when its animals look alien. Modern oceans are built on these relationships. Fish chase smaller fish, crabs break shells, worms hide in sediment, squid watch with elaborate eyes, corals, clams, snails, and sea stars all live within networks of feeding and defense. The Cambrian does not contain the modern ocean, but it begins to establish its deepest pattern. Life is no longer only arranged around the physical environment, it is arranged around other life. The first pursuit gives the sea a new tension, and from that tension comes much of its strange beauty. The animals that survive are not simply those that exist in the right place. They are those that respond to being noticed, touched, followed, resisted, or consumed. In the soft light of the early Cambrian shallows, a shadow passing over the sediment can now matter. A movement in the water can now mean danger. A harder surface can now mean survival. The ancient ocean becomes watchful before it becomes crowded with giants. It becomes reactive before it becomes familiar. And as predation spreads through its communities, the open niches of the Cambrian are no longer just spaces waiting to be filled. They are contested spaces, shaped by hunger, caution, and the beginning of fear without thought. From this point forward, life will not only adapt to Earth, life will adapt to itself. Before the Cambrian Sea becomes famous for shells, spines, grasping limbs, and strange predators, it must first become a world in which information matters. In older marine communities, many organisms can survive by remaining in place, spreading across a surface, filtering water, absorbing nutrients, or moving slowly through microbial films. They respond to chemistry, touch, gravity, current, and light. But they do not yet live in a world where a distant shape may be a threat, a meal, or a rival. With the rise of active movement and predation, the water itself begins to carry meaning. A shadow is no longer only a change in brightness. It may be the approach of another animal. A flicker across the sediment may not be random motion. It may be prey vanishing into a burrow. To survive in this new sea, bodies need ways to gather signals before contact occurs. This is where vision, even in its simplest forms, becomes one of the great quiet revolutions of the Cambrian. The first eyes were not like the eyes of later fish, trilobites, squid, or mammals. They were probably modest structures, patches of light-sensitive cells that could tell brightness from darkness or sense the direction from which light arrived. Such organs do not form an image in the rich modern sense. They do not see a detailed world. But even a small ability to detect light can be useful. It can help an animal know which way is up. It can guide it towards shallow water where food from photosynthetic life is more abundant. It can warn of sudden shadow. It can help regulate daily rhythms in a world already turning beneath the sun. In a calm sea without many active predators, this kind of light sense may be enough for orientation. In a sea where animals begin to chase and avoid one another, it becomes the foundation for something more urgent. A patch of cells that senses light can deepen into a cup, and a cup can reveal direction more precisely. A narrow opening can sharpen the signal. A transparent covering can protect the sensitive surface. A curved lens can gather and focus light. Evolution does not need to foresee the camera eye. It only needs each small improvement to help its bearer survive or feed a little better than others of its kind. This gradual path helps explain why eyes could evolve more than once in separate lineages. The broad idea is called convergent evolution, when unrelated or distantly related groups arrive at similar solutions because they face similar problems. Light behaves according to physical rules. A body that wants to detect it must solve certain problems again and again. It must receive photons, compare signals, protect delicate tissue, and connect the information to movement. The details can differ, but the pressure is shared. In the Cambrian, that pressure grows stronger because seeing changes what an animal can do. A predator that can detect prey at a distance no longer has to wait for accidental contact. It can choose direction. It can track movement. It can aim its body toward a target. A prey animal that can detect a predator gains a few moments of warning, and in a small body, a few moments may be enough to dive, curl, retreat, or freeze. Vision therefore does not belong to hunters alone. It belongs to the relationship between hunter and hunted. Once one side gains it, the other side is drawn into the same new field of awareness. The sea becomes less like a dark room filled with touch, and more like a dim landscape of signals. This transformation can be seen most vividly in the arthropod lineages of the Cambrian. Arthropods are animals with segmented bodies and jointed appendages, and many of them also carry hard outer skeletons. Among their descendants today are insects, crustaceans, spiders, and many other familiar groups, though the Cambrian forms often look unfamiliar. Some early arthropods develop compound eyes, made of many small visual units that sample the world in pieces. The later trilobites will become famous for their mineralized eyes, but even before trilobites dominate the imagination, the Cambrian record shows that visual systems can become elaborate. Some radiodont predators possess large eyes with many lenses, suggesting that sharp vision played an important role in their hunting. The details of these eyes reveal not only anatomy, but behavior. A large visual system is costly. It requires tissue, energy, and a nervous system able to process signals. When an animal invests in such a structure, it suggests that the information gained is worth the price. In the Cambrian Ocean, vision begins to pay its way. The rise of eyes also helps reshape the front of the body. For a moving animal, the front is the first part to encounter food, danger, obstacles, and current. Concentrating sensory organs near the front allows information to arrive where decisions begin. This trend, known as cephalization, is the development of a more distinct head region, with sensory and nervous tissues concentrated there. It does not happen in all animals in the same way, and many successful body plans remain simple or radial. But for animals that move directionally, a head becomes useful. Eyes near the front can guide appendages, mouth parts, swimming movements, or escape responses. The animal is no longer merely a body in water. It has an orientation. It has a forward edge, a way of meeting the world. That change is subtle, but it helps create the feeling of animal life as it is recognized today. The Cambrian seas contain many beings that are still strange, but some now have a direction of attention. They face things. They pursue or withdraw. They turn toward opportunity and away from danger. Light itself may have been different in these shallow habitats. Water filters colour and brightness. Sediment clouds the view. Storms disturb the bottom, microbial surfaces, suspended particles. And the angle of the sun all change what can be seen. Vision in such settings would not always mean clear images across long distances. It may have meant contrast, motion, shadow, and nearness. But those are exactly the signals that matter in a small ocean world. A burrow opening interrupts the surface. A swimming body breaks the light. A predator passing overhead casts a moving darkness. A shell glints differently from soft tissue. A field of spines alters the outline of a prey animal. Each of these signals can become part of selection. Animals that are easier to detect may be eaten more often. Animals that respond quickly to light changes may survive more often. Animals that use shadow to hide or approach may gain advantage. Once vision exists, appearances begin to matter. Shape, posture, surface, and movement become ecological facts. This may have influenced the evolution of camouflage, warning forms, and defensive silhouettes long before the modern versions of those strategies appear. The Cambrian is not a reef of colourful fishes, but it is already a world where being seen can change a life. There is a strange gentleness in imagining the earliest eyes. They are often discussed as tools of competition, and in many ways they are. Yet they also mark the beginning of a deeper intimacy between animals and their surroundings. To sense light is to be connected to the turning planet, to the depth of water, to the presence of others, and to the boundary between open space and shelter. An animal with even simple vision lives in a larger world than one limited to touch alone. Danger arrives sooner. Food exists before contact. The seafloor has direction, contrast, and distance. The ocean is still ancient and alien, but it is becoming perceptible in a new way. The Cambrian explosion is therefore not only an explosion of bodies, it is an expansion of experience. The animals of this time do not think about the world as later vertebrates will, and it would be wrong to place human awareness inside them. But their nervous systems are beginning to organize behavior around signals that travel through water before bodies meet. The result is a sea more alert than any that came before it. In the filtered light above the sediment, small animals carry dark patches, simple cups, and compound surfaces that gather the day into nerve impulses. Some use that information to flee, some use it to feed, some use it only to orient themselves gently through the water column. From these modest beginnings, vision will become one of evolution's most powerful themes, repeated in lineages that will later climb reefs, roam land, fly through forests, and look back at the fossils of this first visual world. But in the Cambrian, it begins quietly. The ocean learns to see one shadow at a time, and once it does, no animal can live quite as invisibly as before. As the Cambrian Sea grows more alert, the bodies within it begin to reveal two very different answers to the same problem. The problem is simple only when stated in the broadest way. How does an animal remain alive when other animals can find it, touch it, wound it, and eat it? Some lineages answer by becoming harder. Others answer by becoming more flexible, more directional, and better able to move away. These strategies do not divide all life neatly, and many animals combine protection with movement in their own proportions. But the contrast becomes one of the defining patterns of early animal evolution. On one side is the outer skeleton, a mineralized or toughened covering that turns the surface of the body into a shield, a support, and sometimes a tool. On the other side is the inner line of motion, the flexible supporting rod and nerve-centered body plan that will, across a long and winding future, lead toward vertebrates. In the Cambrian, neither strategy has reached its later grandeur. There are no crabs with heavy claws, no armored fishes with jaws, no reptiles, birds, or mammals. There are only small marine animals testing the possibilities of hardness and movement in a world where survival has become more demanding. The exoskeleton is one of the most consequential inventions of this time. In arthropods, the outer body covering is not just a shell placed over soft tissue, it is part of the whole architecture of the animal. It gives shape to segments, it provides points where muscles can pull, it protects the inner organs from abrasion, predators, and the roughness of the sea floor. It can carry spines, ridges, plates, and joints. It allows appendages to become levers, paddles, walking limbs, grasping tools, or feeding structures. A soft animal may bend easily, but a jointed animal with a firm exterior can convert muscle contraction into precise movement. This is one reason arthropods become so successful. Their bodies are modular. A repeated segment can be altered in different ways. One appendage can help with swimming, another with sensing, another with feeding, another with walking. Evolution can revise the pattern without having to abandon the whole design. In the early Cambrian, this modularity gives arthropod-like animals an extraordinary range of possible forms. Some remain small and low to the sediment, some swim, some carry shields over the head or body. Some use frontal appendages to gather food, some become predators. The outer skeleton also changes how growth happens. A rigid covering cannot expand smoothly like soft skin. Many arthropods must molt, shedding the old outer layer and forming a new one. Molting is risky. A newly molted animal may be soft, exposed, and vulnerable until the new covering hardens. Yet the reward is great enough that the strategy persists. Each molt allows growth, repair, and sometimes a change in proportions. It also leaves behind durable remains, which is one reason arthropods become so visible in the fossil record. Their armour, once shed or broken, can settle into sediment and enter deep time as a fragment of an ancient life. The seafloor of the Cambrian is therefore not only inhabited by armoured animals, it is gradually littered with the traces of armour, the pieces of bodies that outlast the bodies themselves. This gives the period part of its fossil richness and part of its visual character. Hardness makes life more preservable, and preservability makes the Cambrian seem especially sudden and crowded from the distance of the present. But hardness is not only a gift to paleontologists, it is a living response to a dangerous world. A predator meeting a tough outer surface must spend more effort to break, swallow, or manipulate its prey. A small spine can make a mouthful awkward. A curved plate can deflect attack. A shell can buy time. Even partial armour can shift the balance between death and survival. At the same time, armour can become a burden. It may slow the animal, limit flexibility, or require minerals that must be drawn from seawater. It can make the body heavier and growth more complicated. The success of exoskeletons comes from balancing these costs against protection and mechanical control. In many Cambrian lineages, the balance proves powerful. The arthropod pattern in particular becomes one of the great enduring designs of animal history, not because it solves every problem, but because it can be modified to solve many different problems. While the armoured outside becomes one answer, another answer forms along a quieter path. Early chordates do not dominate the Cambrian seas. They are not the largest animals, not the most heavily protected, and not the most visibly strange. Their importance is easier to recognise only from the far side of time. A chordate is defined by features that may be subtle in a small fossil, including a flexible supporting rod called a notochord, a nerve cord along the back, and patterns of muscle and body organisation that allow efficient bending. In early forms, this design produces a slender, mobile animal that can swim by passing waves of motion along the body. This is not armour, it is escape. It is positioning. It is the ability to slip through water with a kind of simplicity that does not require heavy plates or jointed limbs. In a sea where larger arthropods and other active animals are becoming more dangerous, the chordate strategy may have favoured small size, flexibility, and speed. The notochord is especially important because it gives the body a supportive axis without locking it into stiffness. Muscles can pull against it, bending the body from side to side. A nerve cord coordinates movement. A front end can carry sensory structures and feeding parts. The result is not yet a fish in the familiar sense, but it is a body plan with immense future potential. Later vertebrates will replace and surround parts of this early support system with backbones, skulls, fins, jaws, ribs, and limbs. But the Cambrian beginning is modest. It is a thread of motion running through a soft body. It does not announce itself as destiny. It simply works well enough to persist. The contrast between exoskeleton and caudate flexibility is therefore also a contrast between two ways of meeting the same ecological tension. An armoured arthropod can survive by resisting force, by using jointed tools, and by turning its surface into a working machine. A small caudate can survive by reducing the need to be struck at all, by sensing, swimming, and bending away from danger. The armoured animal may occupy the surface, grasp food, process prey, or defend itself in direct contact. The flexible swimmer may live in the spaces between, moving through water, avoiding the bottom, feeding on small particles or organisms, and escaping from animals that depend on catching and holding. Neither strategy is superior in every setting. The Cambrian Sea rewards variety, not one perfect form. In some places, a hard shell is the better answer. In others, a narrow body and quick movement matter more. Across generations, these answers become lineages, and lineages become the architecture of future ecosystems. There is also a deeper connection between armour and motion. The rise of one can encourage the refinement of the other. Better armour can force predators to become more precise or stronger. Better predators can make prey invest in thicker coverings, sharper spines, deeper burrows, or faster escape. A flexible body may avoid a heavily armoured predator, while a grasping arthropod appendage may evolve to catch flexible prey. These strategies do not develop in isolation. They are part of the same living conversation that began when animals started to matter to one another as food, threat, and obstacle. The Cambrian Explosion is often remembered for the strangeness of its forms, but beneath that strangeness are practical negotiations with reality. A body must hold together. It must move enough to feed or reproduce. It must not be too easy to destroy. It must grow, sense, and repair itself. Armour and motion are two of the most enduring answers to these needs. In the filtered light of the Cambrian shallows, these answers appear in small and early forms. A jointed creature moves across the sediment under a protective surface. A soft caudate flicks through the water with a flexible line running along its back. One carries its skeleton outside, exposed to the world as shield and machinery. The other carries a faint internal axis, a promise of movement more than protection. Around them, the sea continues to fill with shells, traces, shadows, burrows, and eyes. The age of purely soft stillness is fading. The animal body is becoming engineered by conflict, chemistry, and opportunity. Hard surfaces and supple spines mark two directions into the future, and both will endure far beyond the Cambrian. One will lead to trilobites, crustaceans, insects, and countless jointed forms. The other will pass quietly through early fish-like animals and eventually into every vertebrate line. At this moment, however, they are only beginnings, small solutions in an ancient sea, finding their way through a world that has become more watchful and less forgiving. The first hard parts of the Cambrian do not arrive as grand monuments. They arrive as fragments, small curves, caps, tubes, plates, spines, cones, and scales scattered through ancient sediment like the broken alphabet of a new biological language. Paleontologists call many of them the small shelly fauna, not because they all belong to one group, but because they share a way of appearing to the present. They are tiny mineralized pieces from many kinds of animals, often separated from the bodies that made them, often difficult to place with confidence. Yet together they mark a deep transition in the history of life. Before this time, most animals were soft enough that death usually erased them unless conditions were unusually gentle. With the spread of shells and hard elements, life begins to leave a more durable record. The sea floor becomes written with mineral evidence: calcium carbonate, calcium phosphate, silica, and other materials become part of animal bodies, turning the chemistry of seawater into protection, support, and sometimes feeding equipment. The result is not only a change in preservation, it is a change in how animals meet the world. A shell is a boundary made stronger, a spine is a warning made physical, a tube is a shelter given shape, a plate is a small wall against pressure, abrasion, and teeth that are not yet teeth in the later vertebrate sense, but are already part of the new problem of being eaten. The small shelly world is therefore both delicate and serious. Its fossils can be almost dust-sized, yet they record the moment when animal softness began to arm itself. Many of these early hard parts are difficult to connect to complete animals because the Cambrian fossil record is uneven. A storm may scatter shells away from soft tissue. Currents may sort fragments by size. Chemical processes may dissolve one material while preserving another. Later burial may crush, distort, or separate pieces that once fitted together. For that reason, the small shelly fauna can feel mysterious, like finding a field of ancient tools with no makers standing beside them. Some belong to early mollusks, animals related in a broad way to later snails, clams, and squids. Some may have belonged to brachiopods, marine animals with two shells that superficially resemble clams, but have a different internal organization and a different evolutionary history. Some came from tube-dwelling creatures. Some were elements of armored worm-like animals. Some belong to lineages that vanished without leaving familiar descendants. They are not a single cast of characters, but a crowd of beginnings. Their importance lies in their variety. Evolution is not merely adding one kind of shell to one kind of body. It is testing mineralization again and again in different materials, shapes, positions, and functions. A small cap may protect the upper surface of a crawling animal. A cone may shield a soft body tucked beneath it. A tube may anchor an animal in place while it feeds from passing water. A spine may make swallowing difficult. A series of plates may allow flexibility while covering vulnerable tissue. Each solution reveals a slightly different negotiation between defense, movement, feeding, growth, and the chemistry of the surrounding sea. The mineralized shell also changes the relationship between an animal and the sediment. A soft body presses into mud and is easily damaged by grains, currents, and the movements of other animals. A hardened edge can lift tissue, scrape surfaces, or stabilize posture. A tube can raise a feeding animal above the sediment water boundary, where currents bring suspended food. A shell can protect against being buried or disturbed. In the early Cambrian, when the sea floor is being remade by burrowing and grazing, these advantages matter. The world beneath the water is no longer a smooth, mat-covered surface. It is increasingly broken, churned, and occupied. Hard parts allow animals to participate in that changing world rather than merely endure it. Among the more recognizable members of this mineralizing turn are early mollusk-like forms. The deep ancestry of mollusks reaches into this Cambrian complexity, though the exact placement of many fossils remains debated. Later mollusks will become one of the most diverse animal groups on Earth, producing grazers, filter feeders, burrowers, swimmers, reef dwellers, and intelligent predators. In the early Cambrian, their story begins more humbly, with small shells and soft bodies moving across or within the sea floor. A simple shell over the back can protect organs while leaving a muscular underside free for movement. A rasping feeding structure, in later mollusks called a radula, will become one of the great tools of grazing life. though its early evolution is not always easy to trace in stone. What matters in this section of deep time is the gathering of traits that make a small animal more durable, more mobile, and better able to exploit surfaces others cannot use as effectively. Brachiopods also enter the Cambrian record as part of this shell-bearing expansion. They build two valves around a soft body and often live attached to the seafloor or resting upon it, filtering particles from the water. In later Paleozoic seas, brachiopods will become abundant and important, filling ancient marine landscapes with shell forms that resemble clams to an untrained eye. Yet their ancestry is separate, and their bodies are organized differently. The Cambrian beginning of brachiopods shows how suspension feeding can be paired with protection. To filter the water is to depend on exposure to currents, but exposure brings risk. A shell allows the animal to open to feed and close against danger. This rhythm, open and closed, vulnerable and defended, becomes one of the quiet patterns of marine life. Trilobites, too, belong to the broader story of hard Cambrian surfaces, though their most famous rise is larger and more visible than many of the tiny small shelly fragments. They are arthropods with segmented bodies, jointed limbs beneath them, and a mineralized upper shield divided into a central axis and side lobes. Their name comes from this three-lobed appearance. Trilobites will become among the iconic fossils of the Paleozoic. But their early Cambrian emergence belongs to the same world of mineral defense and ecological experimentation. A trilobite body combines armor with articulation. It can protect itself while still allowing movement. Some later forms will enroll, curling the body so the hard upper surface shields the softer underside. Even in their early diversity, trilobites show how a skeleton can be more than a wall. It can be a flexible system, a way of structuring the body into repeated units that can crawl, feed, sense, and survive along the sea floor. The spread of hard parts may also be connected to seawater chemistry. Oceans are not chemically constant through Earth history. The availability of ions, the balance of acidity and alkalinity, and the cycling of carbon, phosphorus, calcium, and other elements can influence how easily organisms build mineral structures. But chemistry alone does not explain why animals mineralize. The materials must become useful in the context of life. A sea rich in the ingredients for shells does not automatically produce shell-bearing animals unless bodies have reasons and mechanisms to use those ingredients. In the Cambrian, those reasons are abundant. Predation, sediment disturbance, competition for space, and new feeding methods all make hard structures valuable. Developmental systems provide ways to grow them. The result is a convergence of planet and organism, geology entering biology through shell, spine, and plate. There is a quiet irony in the small shelly fauna. Many of the animals that produced these fossils were probably modest, even fragile when alive. They moved through shallow seas in bodies measured by small lengths, feeding, hiding, growing, and dying without grandeur. Yet their hard parts change the scale at which life could be remembered. A soft animal may vanish completely. A tiny shell may persist for hundreds of millions of years. Because of this, the small shelly record makes the Cambrian appear more crowded. Not falsely, but newly visible. It is as though life has learned to leave signatures durable enough for stone to keep. These signatures are incomplete and often frustrating, but they are also intimate. A single spine can imply a predator. A tube can imply a current. A shell fragment can imply a body plan, a habitat, and a moment of ancient risk. The small shelly world is not separate from the beauty of the Cambrian explosion. It is one of the reasons that beauty becomes knowable. Before the giant radiodonts take focus, before the strangest soft-bodied fossils reveal their improbable limbs, the tiny mineral pieces show that the animal kingdom is becoming materially inventive. The ocean is filling not only with new shapes, but with new textures: glossy, ridged, plated, roughened, pointed, coiled, and curved. Soft flesh remains at the center of every animal life, but it is increasingly hidden, bordered, and supported by matter drawn from the sea itself. In those small, hard parts, the Cambrian acquires a new soundless sharpness. The age of vulnerable surfaces is not over, but it is no longer alone. The first shells do not end danger. They make danger more complicated. They give prey a chance, predators a challenge, and evolution a richer set of materials with which to work. From fragments smaller than a fingernail, an armoured world begins to assemble. The first radiodonts enter the Cambrian story like shapes assembled from several futures at once. They are arthropod relatives, but not arthropods in the familiar modern sense of crabs, insects, or spiders. They belong near the early branching lines of that vast group, close enough to reveal the beginnings of the arthropod experiment, yet strange enough to resist easy comparison. Their bodies carry a combination that seems almost dreamlike from the present: a pair of large, grasping appendages at the front, a rounded mouth made of hardened plates, a segmented trunk bordered by swimming flaps, and often large eyes set for active searching. They are not the only predators in the Cambrian Sea, and not every radiodont lives in exactly the same way. But they show that predation has moved beyond small, hidden pressures. It has become visible as architecture. A radiodont body is built around finding, approaching, and handling food in open water or near the sea floor. The name means radiating tooth, a reference to the circular mouth parts that once puzzled researchers when isolated fossils were found without the rest of the animal. Like so many Cambrian creatures, radiodonts were first known in pieces. A frontal appendage could seem like the body of a shrimp. A mouth cone could seem like a jellyfish. A trunk fragment could be misread as something unrelated. Only later did these scattered parts come together into a single animal, and the reconstruction changed the feeling of the Cambrian Sea. It revealed that some of its inhabitants were not merely odd, but powerfully organized for a new kind of ecological role. The frontal appendages are the most immediate clue. In different radiodont species, these limbs vary in shape, length, curvature, and the arrangement of spines. Some appear suited for seizing active prey. Others may have raked through sediment, swept small organisms from the water, or filtered particles. This variety matters because it shows that radiodonts were not a single design repeated across the ocean. They were a radiation of their own, a set of related forms exploring different feeding strategies within the expanding Cambrian world. Still, the predatory radiodonts hold a special place because they bring together several traits that the arms race had made valuable. They can see, they can swim, they can reach forward, they can bring food toward a mouth reinforced by hard elements. In earlier communities, an animal might wait for food to arrive or graze along a surface with limited range. A radiodont can search. Its body suggests direction and intention, though the intention is only biological, written in nerves and muscles rather than thought. The swimming flaps along the trunk give these animals a fluid way of moving through water. They may have undulated in coordinated waves, allowing the body to glide, turn, rise, or descend with more grace than a heavy armoured crawler. In a sea where many animals remain close to the sediment, even moderate swimming ability can open a new layer of habitat. The water column itself becomes a hunting ground, a pathway, and a vantage point. A predator above the bottom can approach from angles that benthic animals are not built to monitor. It can patrol along the boundary between open water and sea floor. It can exploit animals that rise to feed or disperse. The Cambrian Ocean, once understood mainly as a surface of mats and sediments, gains vertical depth as animals begin to use the space above it more actively. Radiodonts help make that space dangerous. Their eyes reinforce this impression. Some radiodont fossils preserve evidence of large compound eyes with many visual units, suggesting a capacity to detect detail and movement better than most animals around them. A visual predator changes the behavior of everything within reach. Prey no longer has to be touched before it is at risk. It can be seen from a distance, followed, and intercepted. The evolution of such eyes also implies a nervous system capable of using visual information in real time. Movement and sight must work together. A hunter that sees but cannot turn effectively gains little. A swimmer that moves well but cannot detect targets is limited by chance. Radiodonts unite these abilities in a way that feels decisive for the Cambrian. They are not merely larger mouths. They are mobile sensory platforms, bringing perception and action into a single predatory design. This does not mean they were invincible. Cambrian predators still lived within the constraints of their bodies and environments. Their mouthparts may not have crushed every shell with ease. Their appendages were shaped for particular prey sizes and behaviours. Their soft parts remained vulnerable to injury, disease, and the risks of molting or growth. The sea itself could be cloudy, turbulent, oxygen-limited, or crowded with obstacles. Yet within those limits, radiodonts mark a new level of ecological pressure. The presence of a swimming hunter with grasping limbs makes defensive spines more meaningful. It makes burrowing more useful. It makes hard shells more valuable. It rewards animals that can detect shadows, cling tightly, curl, hide, or move in unpredictable ways. The radiodont does not need to consume every animal to shape the community. Its possibility is enough. The risk of being caught alters evolution even for those that are rarely caught. There is also a quiet lesson in the way radiodont fossils were misunderstood. The Cambrian does not offer the past in complete portraits. It gives fragments first, and the mind tries to fit them into familiar categories. A grasping appendage found alone may look like one animal. A mouth found alone may look like another. The deeper body plan only appears when enough pieces are gathered from enough places and compared with enough care. In this sense, radiodonts are not only predators of the ancient sea, they are reminders that the history of life has to be reconstructed from partial evidence, and that strangeness often comes from seeing only part of the truth. When the pieces align, the animal becomes more coherent, but not less wondrous. It is strange because it is real in a way that modern categories cannot fully soften. The radiodont dawn also reveals that Cambrian beauty is not only gentle or delicate, it includes the beauty of function sharpened by need. The curve of an appendage, the spacing of spines, the placement of eyes, and the rhythm of swimming flaps all express the same quiet fact. Bodies are shaped by the problems they survive. A radiodont is beautiful not because it is harmless, but because it shows life becoming precise under pressure. It is a predator, yet it is also a swimmer, a sensor, a product of seawater chemistry, developmental inheritance, and ecological opportunity. It belongs to a world in which animals are beginning to make other animals more elaborate. In its grasping limbs can be felt the response of armoured prey. In its eyes can be felt the first importance of distance. In its swimming body can be felt the opening of the water column as a new stage for animal life. Some radiodonts may have been among the largest animals of their communities, especially by early Cambrian standards, though size varied across the group and later giants deserve their own place in the story. Their presence would have changed the scale of fear in small seas. A worm in the sediment, a trilobite along the bottom, a soft animal resting under a thin covering of mud, or a small swimmer near the surface all exist differently when a radiodont can pass nearby. Fear here should not be understood as a human feeling. It is a pattern of selection. Bodies that behave as if danger matters leave more descendants when danger truly does matter. Reflexes, shells, burrows, spines. And escape movements become the biological equivalents of caution. The radiodont is part of the reason such caution spreads. Its body turns predation into a visible force, and from that force comes more variation. The early Cambrian sea is therefore not only filling with new animals, it is filling with consequences. Each successful predator creates a shadow in which defensive life evolves. Each defensive innovation creates a challenge that may refine predation further. Radiodonts stand near the beginning of this long exchange. They are not ancestors of all later hunters, and their own lineages will eventually fade, but the ecological role they reveal never disappears. Active pursuit becomes one of the enduring themes of animal history. Later oceans will have jawed fish, cephalopods, marine reptiles, sharks, and whales. None of those forms exists in the Cambrian, yet the principle that will support them is already present. A body can move through water in search of other bodies. It can use senses to reduce uncertainty. It can carry tools for capture at the front of itself. It can turn the open sea into a place of encounter. In that sense, the radiodont dawn is not merely the rise of a strange arthropod relative. It is the moment when the Cambrian ocean grows a predatory silhouette. The small shelly world, the burrowed sediment, the soft survivors, and the early armoured crawlers now share their environment with animals built to hunt them. The water above the sea floor is no longer only a medium of currents and light. It is crossed by watching bodies with flaps and claws, moving through the blue-green shallows of an ancient planet. Life has become more beautiful, but also less innocent. The Cambrian sea is learning that form can follow hunger. The Cambrian sea is often remembered through its icons: the trilobite with its many segments, the radiodont with its frontal claws, the small shells that mark the arrival of mineralized defense. Yet some of its most revealing animals are the ones that seem least willing to fit into any familiar frame. They appear in the fossil record like messages from a version of nature that tried many designs and kept only some of them. Their bodies can seem awkward, impossible, almost playful. But that strangeness is partly an illusion created by distance. An animal looks bizarre when its relatives are gone, when its habits are hidden, when only a flattened trace remains in stone, and when the living world that made sense of its shape has disappeared. In the Cambrian, these forms were not jokes or mistakes. They were working organisms, feeding, moving, defending themselves, and reproducing inside real ecosystems. Their beauty comes from the fact that they were both strange and practical. They show that evolution does not aim for the familiar, it only explores what can survive. Among the most famous of these experiments is hallucigenia, a small animal whose name has become almost inseparable from Cambrian oddity. The fossil is narrow, worm-like, and lined with long paired structures that once confused interpretation so deeply that its upper and lower sides were not immediately clear. At first glance, it seems less like an animal than a row of spines and soft extensions arranged around a thin body. For a time, reconstructions placed it upside down, with stiff spines imagined as legs and flexible appendages interpreted in stranger ways. Later study turned the creature over, clarified its orientation, and brought it closer to a group of soft-bodied animals related to velvet worms. Cambrian animals are difficult not because they are nonsense, but because they preserve body plans near the base of lineages that later changed, narrowed, or vanished. Hallucigenia is not impossible. It only lacks a living counterpart close enough to make it instantly obvious. Its spines, once so puzzling, become more understandable when placed inside a world shaped by predation. A small, soft animal crawling along the seafloor would be vulnerable to grasping appendages, probing mouthparts, and searching predators. Long defensive spines could make it harder to swallow or manipulate. They could raise the apparent size of the animal or turn it into a painful mouthful. The soft lobed limbs on the opposite side could help it move slowly over microbial surfaces or sediment. Its body does not need to be graceful by modern standards. It only needs to solve the problems of its own habitat. It is a delicate solution to danger, made in the materials available to a small animal in a crowded shallow sea. The same principle applies to many other Cambrian forms that seem strange from afar. Some have rows of plates like flexible armour. Some carry bundles of spines. Some look worm-like but wear mineralised scales. Some have feeding structures unlike anything common in modern oceans. Others combine soft bodies with small hard parts in ways that make them difficult to assign to known groups. The Burgess Shale and other exceptional fossil deposits preserve such animals because rare conditions buried them quickly and protected soft tissues from ordinary decay. Without those deposits, many would be known only from fragments or not known at all. This matters because the Cambrian explosion was not only an explosion of shells, it was also an explosion of soft anatomy, and soft anatomy is usually the first thing the planet erases. The famous strangeness of Cambrian life is partly a gift from unusual preservation. For a brief window, stone kept more of the animal than stone usually keeps. It kept limbs, outlines, guts, spines, eyes, and the hints of muscles. It allowed the present to see experiments that would otherwise have vanished completely. These experiments also remind the modern mind that the categories used for animals today are survivors' categories. The living world is shaped by the lineages that pass through extinction filters. Arthropods, mollusks, chordates, echinoderms, annelids, and other major groups feel natural because they remain. But during the Cambrian, the boundaries among early branches were not always so easy to recognize. Some animals sit on stem lineages, meaning they are related to the ancestry of a major group but fall outside the living crown of that group. A stem arthropod may show some arthropod traits without having the full set seen in later forms. A stem onychophron may resemble velvet worms in certain ways but not match them exactly. This can make the Cambrian feel like a hall of almost familiar beings. They are not failed versions of modern animals. They are relatives near branching points, carrying combinations that later evolution separated, refined, or abandoned. The beauty of such forms lies in their incompleteness from the present perspective and their completeness in their own time. They were not waiting to become something else. They were already themselves. Hallucigenia and its companions also reveal how defense can become ornament to later eyes. A spine may look decorative in a fossil photograph, especially when the danger that shaped it is gone. A plate may look like pattern. A row of lobes may seem whimsical. But in the living sea, these features had weight, texture, and consequence. A predator approaching a spiny animal encounters a physical problem. A body with plates bends differently from a naked worm. A creature with raised projections casts a different outline in filtered light. Even features that appear extravagant may be ordinary answers to attack, support, movement, or feeding. The Cambrian did not produce strangeness for its own sake. It produced variation and predation, sediment disturbance, oxygen gradients. An ecological opportunity sorted that variation. Some shapes persisted, many did not. When a lineage disappears, its body plan can later seem like an evolutionary riddle, even if it once made perfect sense in a specific setting. This is why extinction changes the meaning of form. A living animal is surrounded by context. An extinct animal is surrounded by questions. There is a calm humility in studying these forms. The first reconstruction may be wrong. The apparent top may be the bottom. A supposed limb may be a spine. A mouth may be found only after better specimens are examined. The Cambrian asks for patience because its animals do not always obey expectations built from modern seas. Science moves by correction here, not by embarrassment, but by refinement. Each new fossil, each new imaging method, and each new comparison with living animals can soften an old mystery. Hallucigenia, once almost absurd in its reconstruction, becomes a small lobopodian with defensive spines and clawed limbs. Other strange animals likewise become less alien when their details are understood, yet they never lose all of their wonder. Explanation does not diminish them. It makes their strangeness more intimate, because it shows how deeply real they were. They had fronts and backs, surfaces and vulnerabilities, feeding needs and developmental histories. They were not symbols of chaos. They were citizens of a complex sea. Their existence also widens the meaning of the Cambrian Explosion. If the story is told only through the lineages that lead to later success, it becomes too narrow, almost too tidy. The Cambrian was not simply the beginning of modern animal groups. It was a broad ecological trial in which many forms entered the world, interacted, adapted, and vanished. Some left descendants, some left only impressions. Some may have been abundant for a time and then erased by later turnover. Their disappearance does not make them irrelevant. Extinct experiments help define the possibilities that evolution explored. They show the width of the search. The lost forms are part of the event's meaning because they show how much larger the original field of possibility was. In the shallow water, a creature like Hallucigenia may have moved slowly among microbial films, sponges, shelly fragments, and other small animals, carrying its defensive architecture through a world of shadows and touch. It would not have seemed strange to itself, because strangeness belongs to observers separated by time. Its spines would have been ordinary burdens. Its limbs would have been ordinary tools. Its body would have met the sediment, the current, and the risk of predators with whatever competence evolution had given it. Around it, other experiments unfolded armoured worms, early arthropod relatives, soft animals with uncertain affinities, and lineages that would later be trimmed away by extinction. The Cambrian Sea was not designed around the modern eye. It was an open workshop of living form, and many of its creations were temporary. Yet temporary does not mean meaningless. A short-lived lineage can still shape food webs, influence predators, leave fossils, and reveal the creativity of natural selection under unfamiliar conditions. The strange experiments of the Cambrian are therefore not side notes. They are central to the atmosphere of the age. They make the explosion feel less like a straight road toward the present and more like a branching garden beneath ancient light. Some branches will thicken into the great trunks of animal history. Others will end in stone. For a moment, all of them share the same sea, and the world becomes crowded with bodies that are practical, vulnerable, and beautiful in ways the present has nearly forgotten. Beneath the visible drama of Cambrian eyes, armour, and grasping predators, another revolution is taking place in the sediment itself. It is quieter than the rise of swimming hunters, and less spectacular than a body covered in spines. But it changes the sea floor from a surface into a layered habitat. Animals begin to enter the mud and sand with increasing persistence. Some move just below the surface, tracing shallow paths through microbial films. Others probe downward, making tubes, galleries, and resting spaces where soft bodies can feed or hide. To a modern observer, a burrow may seem like a simple mark, a line in sediment rather than a body. But in deep time, burrows are among the most important records of behaviour. They show that animals are no longer only living on the world. They are modifying it from within. The sediment becomes shelter, feeding ground, nursery, and refuge. It becomes a place where danger can be delayed by a few body lengths of mud. In the Cambrian, that small delay can matter deeply. The open sea floor is now more dangerous than it was in the Ediacaran. Predators patrol above it, crawlers cross it, and visual hunters may notice motion against its surface. A soft animal lying exposed on top of a microbial mat is easier to find, easier to seize, and easier to tear. Moving downward offers a different set of odds. Beneath the surface, light fades quickly. A predator that depends on sight must search for traces rather than bodies. A grasping appendage may reach only so far into sediment before resistance slows it. The mud itself becomes a shield, not absolute protection, but enough to make attack more difficult. Burrowing is therefore one of the early forms of behavioural defence. It does not require a mineral shell or a sharp spine. It requires muscles, body shape, sensory guidance, and a way to tolerate the chemical conditions below the surface. The animal that burrows trades one set of problems for another. It escapes open exposure, but it enters a world where oxygen can be limited. Movement is costly, and the body must push through grains that press back from every side. A successful burrower must be able to breathe or exchange gases in confined spaces. It must keep its passage from collapsing or be able to move through collapse. It must find food without the clear access of the open surface. It must know when to remain hidden and when to emerge. These demands shape bodies subtly. Elongated forms slide more easily through sediment. Bristles, limbs, muscles, and body waves can help pull or push the animal forward. Some burrows may be lined with mucus or stabilized by repeated movement. Some may open to the surface in ways that allow water to circulate. Others may be temporary, little more than the passing signature of an animal that fed as it moved. Together, these traces reveal a behavioural expansion as important as any shell. The Cambrian substrate revolution is the name often given to this broad transformation. When animals increasingly churn, penetrate, and rework the sea floor. Before intense burrowing, microbial mats can cover sediment in stable sheets, trapping particles and creating firm surfaces. These mats support certain kinds of life, especially organisms that rest upon them, graze them gently, or use their stability. As burrowers expand, the mats are broken. Sediment layers mix. Oxygen moves deeper in some places. Organic matter is buried, exposed, consumed, and redistributed. The boundary between water and sea floor becomes less like a smooth skin and more like a breathing disturbed zone. For older Ediacaran-style communities that relied on broad mat surfaces, this disturbance may have been difficult. For Cambrian animals that could dig, graze, filter, and chase, it created new opportunities. The sea floor became more three-dimensional. Its upper layers turned into an ecosystem of passages and gradients, with chemistry changing over depth so small that they could be crossed by a worm-like body in moments. Burrowing also changes feeding. The sediment is not empty. It holds decaying organic matter, microbes, tiny particles, and chemical energy. An animal that can move through it can feed in ways unavailable to animals restricted to the surface. Deposit feeders swallow sediment and extract what nourishment they can. Others graze microbial films along burrow walls or collect particles brought by water movement. Some animals may have created simple ventilation currents, drawing oxygenated water into their shelters and carrying waste away. Each behaviour alters the environment around it. A burrow is not only a hole, it is a chemical corridor, a place where oxygen, nutrients, waste products, microbes, and small animals interact. Once burrows become common, the sediment itself becomes more alive. It hosts not only the bodies that dig it, but also the microbial communities and small organisms that respond to the new structure. In this way, the Cambrian seafloor becomes an engineered landscape, shaped by the repeated movements of animals too small and soft to be preserved, except by the pathways they leave behind. Predators respond to this hidden world as well. If prey disappears beneath the surface, hunters that can probe, dig, or detect disturbance gain advantage. The strange proboscis of an animal like Opabinia belongs to this larger context, though it deserves its own closer attention. A buried worm, a concealed soft body, or a small animal tucked beneath sediment is not perfectly safe if another animal can search the surface for signs of life and reach down into the hiding place. This creates a second layer of the arms race. It is no longer enough to hide. Some animals must hide better. They may dig deeper, close their openings, move through branching paths, or remain still when danger passes above. Predators, in turn, may become more sensitive to movement, more specialized in probing, or more patient along the sediment surface. The seafloor becomes a landscape of shadows, not only because light fades into mud, but because ecological relationships are now partly concealed. Much of the drama happens out of sight, in pressures, vibrations, chemical trails, and disturbed grains. The fossil record captures this hidden behavior through trace fossils, which preserve activity rather than body parts. A trackway records movement. A feeding trace records repeated contact with sediment. A burrow records the path or resting place of an animal whose body may never be found. Trace fossils are especially valuable because they reveal what animals did, not only what they looked like. They show direction, depth, complexity, and sometimes repeated patterns of behavior. In the Cambrian, traces become more varied and deeper than before. They suggest animals with greater muscular control, more deliberate movement, and more complex relationships with the seafloor. A shell can say that an animal had protection. A burrow can say that it behaved as if the world above it mattered. It can say that the animal sought food in darkness, avoided exposure, or made a home where none existed before. The body vanishes, but the choice remains. There is a special softness in this part of the Cambrian story. Predation and armor can make evolution seem sharp, but burrowing shows survival as withdrawal, patience, and concealment. Not every animal answers danger by becoming harder or faster. Some survive by becoming less visible. Some make safety from sediment. Some turn their narrow bodies through dark spaces and live by the gentle work of processing mud. Their lives may seem modest beside radiodont hunters or elaborate spiny creatures, yet they are foundational. Modern marine sediments are full of burrowing animals, and much of the ocean floor is shaped by their quiet labour. Worms, clams, crustaceans, and many other creatures stir the upper layers, ventilate them, and recycle organic matter. The roots of that living sediment world reach back into the Cambrian transformation. The ancient burrowers are not famous because their bodies are rarely dramatic, but their behaviour helps make the modern sea possible. As the Cambrian Ocean becomes more crowded, the vertical dimension of life increases. Above the bottom, swimmers move through filtered light. On the surface, crawlers, grazers, and shelled animals navigate microbial remains and loose sediment. Beneath them, burrowers create a hidden city of simple tunnels, feeding paths, and temporary shelters. These levels are connected. A predator above influences a burrow below. A buried feeder alters the chemistry that affects surface microbes. A storm may collapse shelters and bury exposed animals alike. A low oxygen layer may limit how deeply life can go. The seafloor is no longer a passive stage beneath evolution. It is an active participant, changed by animals and changing them in return. In the shadows below the Cambrian bottom, the meaning of survival becomes more intricate. A body can endure by disappearing into the planet for a time. It can feed where eyes do not easily reach. It can leave no shell, no face, no famous outline, only a thread through sediment that hardens into stone. Yet that thread is enough to show that life has entered a new relationship with Earth. Animals are not only adapting to the sea, they are rebuilding its floor, grain by grain, passage by passage, in the long quiet beneath the age of strange and beautiful bodies. By the Middle Cambrian, the sea is no longer only a place of openings, pursuits, and first defences. It has become an inhabited world with layers of life arranged across the bottom, within the sediment, and through the water above. The earlier burst of possibility has begun to settle into communities, not settle into stillness, because the Cambrian remains a time of experimentation, but settle into recognisable ecological patterns. There are animals fixed in place, animals crawling between them, animals burrowing below them, animals swimming above them, and predators moving among all of these levels. The shallow continental shelves are now crowded in a way the Ediacaran Sea was not. The old microbial surfaces still exist, but they no longer define everything. They share space with sponges filtering the water, mollusk-like animals grazing or sheltering under small shells, trilobites moving over the sediment, echinoderms beginning their long history of mineral plates and unusual symmetry, and early corals or coral-like builders appearing in forms that hint at later reefs without yet creating the great reef worlds of the future. The result is an ocean that feels alien because its creatures are unfamiliar, yet ecological because their roles are interwoven. A sponge does not hunt. It draws water through its body, capturing tiny particles and releasing the rest back into the sea. In doing so, it turns currents into food and becomes part of the invisible cycling of nutrients. Sponges are among the simplest animals in organisation, lacking the organs and nervous systems that make many later animals so active. But simplicity does not mean insignificance. A sponge can form habitat. It can lift living tissue above the sediment. It can create surfaces where small organisms settle, hide, or feed. Clusters of sponges may have softened currents, trapped particles, and contributed structure to otherwise open sea floor. In a Cambrian community, such stationary bodies help define the landscape. They are like living stones, though softer and more porous, filtering the ancient water patiently. Around them, mobile animals find both shelter and risk. A small crawler may graze near a sponge, avoid a predator by moving among its surfaces, or become exposed in the same place because predators learn to search there. Echinoderms add a different kind of strangeness to this growing world. Their later descendants include sea stars, sea urchins, sand dollars, sea cucumbers, and crinoids. But Cambrian forms often look very different from familiar examples. The defining themes are mineral plates, a water-based system of internal canals used in movement and feeding, and body arrangements that will eventually produce the radial patterns known from modern sea stars. In the Cambrian, these features are still being explored. Some early echinoderms are attached to the sea floor. Some carry plated bodies that do not yet match later symmetry with clarity. Others hint at feeding strategies that rely on currents and suspended particles. Their skeletons are made of calcite plates that can disarticulate after death, scattering into sediment like broken mosaics, while arthropods show the power of jointed armour and chordates, show the promise of flexible motion. Echinoderms show another possibility, a body built from plates and hydraulic control, often slow, often strange, but deeply successful through time. In the crowded Middle Cambrian Sea, they occupy positions that are neither predator in the sharpest sense nor passive mat dweller in the older sense. They are part of the expanding middle ground of animal life, where feeding, anchoring, crawling, and defense are combined in ways that modern categories only partly capture. Trilobites become some of the most visible citizens of this world. Their segmented bodies and mineralized shields preserve well, making them among the most recognizable fossils of the Paleozoic. In life, however, they were not symbols. They were active animals moving across the bottom, feeding, sensing, growing by molting, and responding to a world of danger and opportunity. Some may have scavenged, some may have grazed microbial films, some may have processed sediment, some may have hunted or fed on small organisms. Their diversity eventually becomes enormous. But even early in their history, they show the strength of the arthropod formula. A trilobite has a head shield, a segmented trunk, and a tail region, with limbs tucked beneath the body where they rarely fossilize except in exceptional deposits. Its upper surface is hard and often sculpted, while the underside remains more delicate. This arrangement lets the animal interact with the bottom while carrying protection over its back. Eyes, when present, give it awareness of the water and surface around it. To see a trilobite only as a fossil shell is to miss the living animal beneath, the many legs moving in rhythm, the body responding to sediment, current, and threat. Mollusks and mollusk-like animals add another set of motions to the community. Some carry small caps or shells over soft bodies, some graze across surfaces, some may burrow or rest partly within sediment. The later story of mollusks will include spectacular variety, but in the Cambrian their early representatives help fill the seafloor with low, persistent activity. They scrape, crawl, cling, and protect themselves under mineral cover. Brachiopods and other shelled suspension feeders open and close to the currents, balancing exposure and safety. Worm-like animals continue to move through sediments and along surfaces, some armoured, some soft, some known only through traces. The community becomes more than a collection of body plans. It becomes a network of feeding modes. Water is filtered, sediment is swallowed, microbial films are grazed, prey is seized, organic particles are recycled, waste returns to microbes and chemistry, shells and molts accumulate, burrows ventilate the ground. Every action changes the setting for another. This is what makes the Middle Cambrian feel like a complete biosphere rather than a display of isolated curiosities. Each animal belongs to a pattern of exchange. Early corals or coral-like cnidarians appear in this broader fabric. Though the great coral reef ecosystems known from later periods are not yet the dominant architecture of the sea, cnidarians are the broader group that includes jellyfish, sea anemones, and corals. Their bodies are organized around simple tissues and stinging cells, and many live by capturing small prey or particles. In Cambrian seas, early representatives add still another mode of life animals that may attach, filter, sting, or build small skeletal structures. They suggest that the future of reef building and complex fixed communities is beginning to assemble, but cautiously. The Cambrian Sea is not yet a modern tropical reef blazing with fish and branching corals. It is a stranger, lower, more open world, where sponges, microbial structures, shelly animals, and soft-bodied forms share the burden of making habitat. Its beauty is quieter than a modern reef but no less intricate. Structure is present, but it is provisional. The architecture of life is being tested in patches. What makes this ocean alien is not only the appearance of individual animals, it is the different balance among them. Arthropods hold many of the roles that later fish, crustaceans, and cephalopods will divide among themselves. Chordates remain small and easily overlooked. Sponges and microbial surfaces contribute much of the fixed structure. Echinoderms are present, but their familiar star-shaped descendants have not yet become the image by which the group is known. Corals exist only as early hints of a later ecological power. Many soft-bodied animals belong to branches with no obvious modern equivalent. The whole system is recognizable as an ocean ecosystem, yet displaced from modern expectation. It has feeding levels, shelters, predators, prey, recyclers, and habitat makers. But the cast is profoundly different. This is why the Cambrian can feel like another planet without leaving Earth. It is the same biosphere, earlier in its long process of sorting, before later extinctions and radiations narrowed the visible possibilities into more familiar shapes. In these middle seas, the Cambrian begins to reveal its deeper meaning. The event is not just the appearance of strange animals in quick succession. It is the formation of ecosystems dense enough for those animals to influence one another continuously. A predator changes where grazers move. Grazers change microbial surfaces. Burrowers change sediment chemistry. Filter feeders change particle flow. Shelled animals change what predators can consume. Sponges and attached forms change the physical structure of the bottom. The sea is now full of feedback. Life responds to environment, but it also becomes environment. The body of one animal becomes shelter for another, obstacle for another, food for another, and after death, material for microbes and sediment. Complexity here does not mean intelligence or progress toward a goal. It means interdependence. The Cambrian world is becoming thick with consequences. As light passes through the shallow water, it falls on a bottom crowded with small acts. A trilobite crosses a patch of sediment. A sponge filters without pores. A shelled animal closes against disturbance. An echinoderm rests or feeds with a plated body arranged in a pattern no modern shoreline would make familiar. A soft worm moves below, leaving a trace that may outlast all the bodies above it. Somewhere overhead, a larger hunter moves through the water, and the community subtly reorganizes around that possibility. The alien middle seas are not silent, but their activity is slow when held against human imagination. Their drama is distributed across thousands of small interactions, each one almost nothing by itself, all of them together building the first richly animalized ocean. In that ocean, beauty is no longer only the strangeness of a single fossil. It is the arrangement of life into a working world, fragile, crowded, inventive, and unlike anything Earth had known before. Among the many animals that make the Cambrian Sea feel unfamiliar, Opabinia holds a special place because its strangeness is not grand or monstrous, but precise. It is small, delicate, and almost difficult to believe at first glance, with a soft body, lateral swimming flaps, a fan at the rear, 5 eyes rising from the head, and a long flexible proboscis ending in a grasping claw. It does not dominate the ocean by size. It is not the great apex hunter of the age. Yet it reveals something just as important as power. It shows that Cambrian animals were already becoming specialized. They were not merely random experiments in shape. They were entering narrow roles, using unusual anatomy to solve particular problems in a world where food, danger, and shelter were becoming more finely divided. Opabinia's reach is therefore more than the reach of a single strange appendage. It is the reach of evolution into precision, into the subtle spaces between predator and prey, surface and burrow, swimming and probing, visibility and concealment. The animal itself is known most famously from the Burgess Shale, one of the rare fossil windows that preserves soft-bodied Cambrian life in remarkable detail. Without such deposits, Opabinia might have vanished from scientific memory entirely, because much of its body was too soft and fragile to fossilize under ordinary conditions. In life, it may have moved through the water just above the sea floor, using its side flaps in gentle waves, steering its body through a low, crowded world of sediment, sponges, trilobites, small shelly animals, worm-like creatures, and microbial textures. Its body was not heavily armoured like many arthropods, though it belonged somewhere near the broader early arthropod story. It seems instead to have relied on mobility, sensory awareness, and the extraordinary tool at the front of its body. The 5 eyes suggest that information mattered deeply to its way of life. They may not have created vision as sharp as the later eyes of more advanced hunters, but they likely helped detect movement, light, and the layout of the seafloor below. For an animal that needed to find small prey or edible material among sediment and hiding places, such awareness would have been valuable. The proboscis is the feature that gives Opabinia its peculiar grace. It extended forward from the head like a soft searching arm, ending in a claw-like structure that could grasp or manipulate objects. This was not a jaw in the familiar sense, nor a limb like the jointed appendages of later arthropods. It was a specialized extension, a way of reaching into places where the main body did not have to go. In an ocean where many small animals hid in sediment or among structures on the bottom, a probing appendage could be a powerful advantage. A buried worm-like animal, a soft-bodied prey item tucked into a shallow depression, or an edible particle lodged between surfaces might be reachable by the proboscis before the rest of Opabinia came close enough to risk contact. This gives the animal a particular ecological character. It was not simply chasing in open water, it was searching, testing, and extracting. It may have moved like a small hunter along the boundary between open sea and hidden sediment, using its front appendage to turn concealment into opportunity. This kind of specialization matters because it shows how quickly the Cambrian arms race became refined. Once animals burrowed to avoid predators, the seafloor gained hidden food. Once hidden food existed, other animals could evolve ways to find it. A burrow is a refuge, but it is also a signal that something living may be inside. A disturbance in sediment, a small opening, a chemical trace, or the faint movement of grains could become meaningful to a hunter able to interpret it. Opabinia's anatomy fits this world of partial concealment. Its proboscis suggests a predator or forager adapted not only to seeing prey in the open, but to reaching beyond the visible surface. In that sense, it belongs to the same ecological conversation as burrowing animals. The burrower changes the environment by hiding. The probing animal changes it again by making hiding less secure. Neither form wins permanently. Instead, each creates the conditions for further adaptation. Deeper burrows, better senses, quicker withdrawals, more careful probing, and more specialized mouthparts can all emerge from such relationships. The Cambrian Sea becomes complicated not only because animals are many, but because their strategies overlap in close detail. Opabinia also reminds the present that small predators can be as evolutionarily meaningful as large ones. It is easy to focus on the biggest hunters because scale leaves a strong impression. A giant radiodont sweeping through the water feels like a clear symbol of Cambrian danger. But ecosystems are often shaped just as deeply by smaller animals acting in more specific ways. A small predator that specializes on hidden prey can influence how those prey live. It can select for better burrowing, tougher coverings, chemical defenses, or different feeding times. It can make the surface of the sediment into a zone of uncertainty. It can force animals to treat even slight exposure as risk. In modern ecosystems, many powerful interactions happen at small scales, in crevices, within mud, beneath leaves, inside reefs, or among grains of sand. The Cambrian was no different in principle. Its most memorable animals may be visually dramatic, but its evolutionary engine also turned through tiny encounters, a proboscis reaching into sediment, a soft body withdrawing, a claw closing around prey, and a missed attempt repeated across generations can shape anatomy as surely as any spectacular chase. The 5 eyes of Opabinia deepen this picture. A head carrying several visual organs may seem almost whimsical, but in a complex shallow sea, multiple eyes could help widen the field of detection. The animal may have needed to watch the bottom, while also monitoring the water around it. It may have faced danger from larger predators even as it hunted smaller prey. In a Cambrian community, no creature is only predator or only prey. A small hunter can be hunted. A creature with a grasping appendage can still be seized by something larger. This double position may help explain the layered nature of many Cambrian bodies. They're equipped for action, but also exposed to action from others. Opabinia's soft body and swimming flaps suggest it could move, but not necessarily withstand heavy attack. Its best defense may have been awareness, maneuverability, and perhaps remaining near the bottom where complexity offered cover. In this, it reflects a general truth of animal life. Survival rarely depends on a single trait. It depends on a workable combination. Opabinia's combination was vision, swimming, and reach. The history of its interpretation is also part of its quiet fascination. When first presented to wider scientific attention, Opabinia seemed so unlike familiar animals that it challenged assumptions about Cambrian life. Its body forced researchers to think more carefully about early arthropod evolution and about the many stem forms that do not fit neatly into living groups. The animal looked absurd only because the branches around it had been pruned by extinction. In its own time, it was one variation among many, another body plan moving through the Cambrian Sea with enough success to leave fossils behind. Scientific understanding has placed it within broader evolutionary patterns, but it remains wonderfully distinct. It is not a transitional sketch toward a modern animal. It is a complete creature from a vanished ecosystem, carrying a solution that belonged to its own moment. This is why Opabinia is so valuable to the story. It prevents the Cambrian explosion from becoming too simple. The event was not just the origin of familiar groups, it was the rise of ecological detail, with animals exploring forms that later history would not preserve as living lineages. In the Middle Cambrian Sea, Opabinia may have passed over soft sediment with slow, controlled movements, its flaps lifting and lowering along the sides of its body, its eyes sampling the shifting light, its proboscis held forward like a question posed to the seafloor. Below it, small animals hid, fed, and moved through the mud. Around it, trilobites crawled, sponges filtered, echinoderms rested in plated stillness, and larger predators cast danger through the water. The world was not a chaotic freak show, but a working ecosystem in which even the strangest forms had reasons. Opabinia's reasons were written in reach. It could bridge the gap between water and sediment, between visible and hidden food, between movement and manipulation. That bridge is the essence of specialization. It shows that by this time, life was no longer merely becoming diverse in a broad sense. It was becoming exact. Animals were beginning to fit into roles shaped by the behaviors of other animals. The strange proboscis of Opabinia is therefore a sign of a more mature Cambrian world, one in which niches are subdivided, dangers are layered, and opportunity lies in small differences of access. The animal's beauty is not the beauty of symmetry or familiarity. It is the beauty of a problem solved in a way that would almost never be repeated. In its 5-eyed face and delicate grasping reach, the Cambrian Sea reveals one of its deepest truths. Evolution can be practical and astonishing at the same time. Among the animals of the Cambrian Sea, Anomalocaris carries a different weight from the delicate oddity of Opabinia, or the quiet persistence of small shelly forms. Its name means strange shrimp, a reminder that its fossils were once misunderstood in pieces, with appendages, mouth parts, and body fragments interpreted as separate creatures before they were brought together into a single animal. When reconstructed, it becomes one of the clearest symbols of Cambrian predation, a large radiodont with a streamlined body, broad swimming flaps, stalked compound eyes, paired frontal appendages, and a circular mouth built from hardened plates. By the standards of its time, it was enormous, in a world where many animals were small, soft, low to the sediment, or only lightly armoured. A creature approaching about a metre in length would have been a dominant presence. It didn't have to be monstrous in a theatrical sense. Its importance comes from proportion. The Cambrian Sea had produced a hunter large enough to change the scale of danger. Anomalocaris was not the first predator, and it was not alone among radiodonts, but it gathered several predatory traits into a form that feels unusually complete. Its body suggests swimming strength rather than crawling. Along the sides, flexible flaps could move in waves, giving the animal a smooth passage through the water above the seafloor. This allowed it to search across a larger area than a bottom-bound animal. It could patrol the open layer just above crowded communities, where trilobites, worms, sponges, early echinoderms, shelly animals, and smaller soft-bodied creatures occupied the bottom. Above them, Anomalocaris would have moved as a shadow with direction, a hunter not restricted to one patch of sediment. Its size and mobility made the water column itself more dangerous. For animals that had evolved shells, burrows, spines, or low profiles, the threat now came not only from beside them or beneath them, but from the space overhead. The frontal appendages are central to this image. They extended from the front of the head and carried spines arranged in ways that could help seize, trap, or manipulate prey. In a world where many animals protected their soft parts under mineral surfaces or within sediment, grasping tools were important. A mouth alone cannot easily capture a struggling animal. It needs a way to bring prey close, hold it against resistance, and orient it for feeding. The appendages of Anomalocaris perform that task. They turn the front of the body into a zone of active capture. Their spines could close around prey, rake through small animals, or guide food toward the mouth. The mouth itself, a ring of plates, has sometimes been imagined as a shell-crushing device. Though the details of what it could break remain debated, it may not have been able to crush all trilobite armor with ease. Yet it did not need to defeat every shell to be powerful. Predators usually specialize by possibility and opportunity. Anomalocaris may have taken soft animals, injured animals, molting arthropods, lightly armored prey, or smaller organisms caught in its appendages. A single apex predator does not consume everything in its world. It shapes behavior by making exposure costly. The eyes of Anomalocaris deepen that power. Fossil evidence from radiodont eyes suggests that some members of this group had large compound eyes with many visual units, giving them strong ability to detect movement and form. For a hunter moving through water, vision is more than an accessory. It is the map that makes pursuit possible. A large animal needs information early enough to turn, accelerate, and position itself. Prey that can be seen from a distance is prey that can be approached with intent. In Cambrian waters, where light filtered through shallow seas and sediment could cloud the view, vision would have worked with motion and contrast rather than bright modern clarity. A trilobite crawling across open bottom, a worm disturbed near a burrow, or a soft animal lifted into the water by current could become a pattern against the background. Anomalocaris would not have understood this pattern as a thought. Its nervous system would have translated it into action, into a turn of the body, a sweep of flaps, a forward reach of spined appendages. This unity of seeing and moving is what makes the animal feel so advanced for its world. It is a predator organized around distance. Its presence would have intensified the arms race already underway. A larger visual hunter makes hiding more valuable. It favors animals that burrow deeper, cling more tightly, develop thicker or more awkward armor, carry spines, reduce their exposure, or rely on quick movements at the edge of danger. It may also favor behaviors that are difficult to fossilize: stillness, timing, use of cover, avoidance of open surfaces, or emergence during safer conditions. The fossil record preserves shells and bodies more readily than fear. Yet the pressure of fear without consciousness can still be read in form. Defensive structures become more common and more elaborate. Sediments fill with traces of animals that do not remain exposed. Hard parts accumulate. Opabinia probes the hidden world. Trilobites refine armored movement. Small chordates remain flexible and elusive. Anomalocaris belongs to this network as one of its most visible pressures. It is the kind of animal that makes other animals evolve around the possibility of being found. Yet Anomalocaris was itself part of the same fragile biological fabric. Its size did not remove it from dependence. It required food, oxygen, growth, and reproductive success. It had to move efficiently enough that hunting brought more energy than it cost. It had to survive injury and environmental change. It lived in oceans where chemistry, temperature, and oxygen were not stable in the modern sense, and where local habitats could change with storms, sediment flows, and shifting sea levels. It may have been dominant in some settings and absent or less important in others. The idea of an apex predator should not make the animal seem detached from its world. It was not a ruler standing above ecology. It was ecology made large, a body in which the needs and risks of the Cambrian Sea became concentrated. If prey populations changed, it would feel that change. If oxygen fell, its active body would face limits. If new defenses spread, its feeding opportunities would narrow or shift. Predators are powerful, but they are also vulnerable to the systems they help shape. The history of its discovery gives the animal another layer of meaning, like other radiodonts. Anomalocaris was assembled by science only after confusion. Its frontal appendage was once taken for a shrimp-like animal. Its mouth was interpreted separately. Its body was not immediately connected to those parts. This mistaken beginning is not a failure so much as a reflection of how unfamiliar the Cambrian was. Fossils from this age often preserve organisms outside easy modern comparison, and the mind naturally reaches for known forms. A strange appendage becomes a shrimp, a circular mouth becomes something else. Only when specimens are compared carefully does the larger design emerge. In that design, the Cambrian becomes more coherent and more astonishing. The predator had been there all along, but it had reached the present in fragments, as though deep time had scattered the animal before allowing it to be seen, once assembled. Anomalocaris changed the emotional scale of the period. The Cambrian Explosion was no longer only about the appearance of many body plans. It was also about the appearance of complex food webs with large active predators near the top. This matters because food webs organize evolution. They determine how energy moves from microbes and algae into grazers, filter feeders, scavengers, small predators, and larger hunters. A top predator does not merely add one more species, it creates a hierarchy of risk. It can influence where prey live, when they move, how they grow, and which defenses matter most. In later oceans, large predators will repeatedly shape marine life, from armored fishes to marine reptiles to sharks and whales. Anomalocaris is not their ancestor in a direct line, but it is an early expression of the same ecological role. It shows that within a few tens of millions of years of the Cambrian opening, the animal world had already become layered enough to support a hunter of significant size and ability. Still, Its beauty is not only in dominance, it is in the way its body gathers the themes already unfolding: eyes, motion, armour, predation, and the division of the sea into ecological roles. The flaps along its sides speak of open water. The appendages speak of contact and capture. The eyes speak of distance and attention. The mouth speaks of food made from other animals. Its very reconstruction speaks of the patience required to understand a world that does not resemble the present. In the shallow Cambrian light, a Nomalocaris may have passed over the sea floor while smaller animals adjusted their lives beneath it. Some buried themselves. Some hid under shells. Some relied on spines. Some escaped through flexibility. Some were caught. The ocean had become a place where beauty could be swift and dangerous, where strange forms didn't merely coexist but pressed upon one another with living consequence. A Nomalocaris stands at that turning point, not as a monster from a nightmare, but as a calm fact of deep time, the first great silhouette of hunger moving through an animal sea. While the Cambrian seas are crowded with armoured arthropods, spiny small animals, probing oddities, and large radiodont hunters, another lineage moves through the background with far less spectacle. It is small, soft, and easy to overlook, yet it carries one of the most enduring body plans in animal history. The early chordates do not dominate the Cambrian world. They do not build the strongest shells, hold the top predator role, or leave the most abundant fossils. Their bodies are not obviously impressive beside the strange reach of Opabinia or the commanding outline of a Nomalocaris, but they represent a different kind of success, one rooted in flexibility, directional movement, and an internal line of support. A chordate is not defined by a hard backbone at this early stage. The key feature is a notochord, a flexible rod running along the body, paired with a nerve cord along the back, and muscles arranged in ways that allow the body to bend from side to side. In later vertebrates, this ancient arrangement will be transformed into skulls, backbones, fins, jaws, limbs, and the long anatomical story that eventually includes amphibians, reptiles, birds, mammals, and human beings. In the Cambrian, however, it begins quietly as a way for a small animal to move through water without armour. This quietness is part of its importance. Evolution does not always begin its most consequential paths with grandeur. Sometimes it begins with a slender body flicking through shallow water, avoiding danger by being difficult to catch. Among the early chordate or chordate-like fossils, Hyquichtsthis is especially significant. It comes from early Cambrian deposits in what is now China, and has often been discussed as one of the earliest fish-like animals, though the word fish can be too broad and too modern for such a delicate beginning. It was small, with a simple head region, traces of segmented muscle blocks, possible gill structures, and a flexible body suited for swimming. It did not have jaws. It did not have paired fins like later fishes. It did not wear heavy armour. Its survival strategy was not to meet danger directly, but to move through it. This is a very different answer from the arthropod exoskeleton, where a trilobite carries a mineralized shield and a radiodont carries grasping appendages. An early chordate carries a line of internal organization. It bends, undulates, and escapes. Its body turns muscle into waves, and those waves push against water. In a Cambrian sea filled with increasingly complex predators and prey, this ability may have opened a narrow but lasting niche. Small size can be a limitation, but it can also be a refuge. A small swimmer can occupy spaces that larger animals cannot exploit efficiently. It can feed on tiny particles or organisms, avoid the most crowded surface, and retreat through water with a quick turn of the body. The early chordate condition should not be mistaken for weakness simply because it lacks armour. Softness can be a strategy when paired with speed and manoeuvrability. A hard shell protects, but it also adds weight. Jointed limbs can grasp and crawl, but they also commit the body to certain mechanical arrangements. A slender caudate body gives up heavy defense in exchange for fluid motion. The notochord works like an elastic support, resisting compression while allowing bending. Muscles along the sides contract in sequence, sending curves down the body. This is a simple and elegant way to swim, and it will remain central to fishes and many later aquatic vertebrates. In the Cambrian, such motion would have been modest, but it gave the animal a way to live in relation to currents, predators, and food sources without being tied entirely to the bottom. The water column becomes not only the hunting ground of radiodonts, but also a corridor for small, evasive bodies. The same open space that creates danger also creates possibility. A caudate can move through that space as a thin thread of life, not powerful enough to command the sea, but efficient enough to remain within it. Picaia, known from the Burgess Shale, deepens this thread. It lives somewhat later than Hyquictis, and has long been discussed as a possible early caudate or close caudate relative. Its body was narrow and laterally flattened, with a distinct front end and repeated muscle bands that suggest swimming. It also had tentacle-like structures near the head, giving it a slightly unfamiliar appearance despite its place in discussions of vertebrate ancestry. Picaia is not a direct portrait of the first vertebrate ancestor in a simple straight line. The early branches of caudate evolution are complex, and fossils from this interval are difficult to place with absolute certainty. But Picaia shows the same essential theme: a small animal organized around a flexible axis and side-to-side motion. Its significance comes not from being grand, but from being plausible, from showing how a body without armor could persist among more heavily protected and visually dramatic animals. It is a reminder that the future often travels unnoticed in the present. In a Cambrian community, Picaia would not have seemed like the beginning of anything monumental. It would have been one more small animal among many, vulnerable to predators, dependent on food and oxygen, shaped by the same currents and risks as its neighbours. Only after hundreds of millions of years does its body plan become luminous with meaning. The early caudate story also changes how the Cambrian explosion is understood. The event is not only the origin of hard shells, arthropod success, or strange extinct experiments, it is the beginning of deep anatomical themes that will unfold for the rest of animal history. Internal support, directional swimming, segmented muscles, a dorsal nerve cord, and a defined head region all point toward later vertebrate possibilities. Yet those possibilities must not be treated as destiny. The Cambrian caudates were not trying to become fishes, and fishes were not trying to become land animals, and land animals were not trying to become mammals. Evolution has no memory of future outcomes. It moves through immediate survival. The caudate thread persists because each generation works well enough in its own world. Later significance is added by history, not intention. This makes the lineage more beautiful, not less. Its grandeur is retrospective, a pattern recognized only after the thread has passed through many transformations. At the time, it is simply one more way to survive the Cambrian Sea. The presence of early caudates alongside arthropods also shows that major animal groups were exploring very different mechanical philosophies at the same time. Arthropods place the skeleton outside, divide the body into jointed segments, and use appendages as tools. Caudates place support inside, preserve a more continuous body axis, and use whole-body bending as a central movement strategy. Echinoderms experiment with plates and hydraulic systems. Mollusks combine soft bodies with shells, muscular feet, and feeding surfaces. Worm-like animals burrow and process sediment. The Cambrian Sea is therefore not a competition between one superior design and lesser alternatives. It is a broad exploration of what animal bodies can be. Many solutions endure because the world contains many problems. A bottom crawler, a filter feeder, a swimmer, a burrower, and a predator all need different arrangements of tissue, support, and behavior. The chordate solution is one of these arrangements, modest at first, but unusually open to later transformation. An internal support can be elaborated without enclosing the whole body in armour. A nerve cord can coordinate increasingly complex movement. A head region can gather sensory organs and feeding structures. Muscles can become more powerful. Fins can arise, jaws can appear, and the body can move from small evasive swimmer to active predator in later periods. In the Cambrian, most of that remains far beyond the horizon. Still, the foundation is present. The chordate thread is faint, but it does not break. There is something quietly moving about this line of animals living under the shadow of larger hunters. The Cambrian is filled with forms that seem more impressive in the immediate scene. Anomalocaris commands attention. Trilobites fill the fossil record. Hallucigenia fascinates the imagination. Upperbenia unsettles expectation. But the small chordates carry a different kind of wonder. They are not strange because their bodies are extravagant. They are strange because their simplicity contains distance. In their side-to-side swimming is the earliest motion of a lineage that will one day produce animals with skulls, senses, memory, and eventually the ability to study stone and ask where they came from. That outcome is not visible in the Cambrian water. It is hidden inside ordinary survival. A small chordate swims because swimming helps it live. It avoids a predator, finds food, responds to light or current, and leaves behind only the faintest chance of fossil memory. Around it, the sea continues its restless experimentation. Shells harden, burrows deepen, eyes sharpen, predators widen their search, and many body plans flourish for a time before vanishing. The chordate does not need to win the Cambrian in any obvious way. It only needs to continue. In deep time, continuation can be more powerful than dominance. The giant hunter may disappear. The famous strange form may leave no living branch. The armoured dynasty may thrive for ages and then end. But a small flexible lineage can pass through extinction, radiation, and transformation, carrying its ancient axis forward into worlds not yet made. In the Cambrian sea, that lineage is only a thread, nearly lost among brighter forms. Yet it is one of the threads from which the later animal world will be woven. Its beauty lies in its quietness, in the fact that the future of vertebrates begins not with power, but with movement, vulnerability, and a slender body bending through ancient light. The Cambrian explosion is often remembered as a beginning, but every beginning in deep time is also the start of later loss. The same seas that produce trilobites, radiodonts, small shelly animals, early chordates, spiny lobopodians, echinoderms, mollusks, brachiopods, burrowers, grazers, and delicate soft-bodied experiments also became the setting in which many of those forms disappeared. The Cambrian was not a stable paradise after its great diversification. It was a long interval of changing oceans, shifting climates, fluctuating oxygen, moving shorelines, and ecological pressure. Its life was brilliant, but not secure. By the later Cambrian, the first wide flowering of animal forms had already begun to pass through filters of extinction and replacement. Some lineages continued and became major presences in later Paleozoic seas. Others narrowed. Others vanished so completely that they survive only as impressions in exceptional fossil beds or as isolated fragments of shell and spine. This is the quieter half of the Cambrian story. Life becomes strange and beautiful, and then the world begins to decide which kinds of strangeness can continue. The causes of late Cambrian declines are not reducible to a single event in the way some later mass extinctions are sometimes framed. The rock record points instead toward repeated ecological and environmental disruptions. Sea levels rose and fell across broad continental shelves, changing the amount and quality of shallow marine habitat. Oxygen levels may have shifted, leaving some basins oxygen poor and difficult for active animals. Climate may have fluctuated, perhaps including colder intervals that stressed communities already adapted to particular shelf conditions. Volcanic activity, changes in ocean chemistry, and the cycling of nutrients may also have contributed. These forces did not act separately from life. A drop in oxygen affects larger and more active animals differently from small or sluggish ones. A change in sea level can erase one habitat while opening another. A shift in nutrient supply can alter the base of food webs and ripple upward into grazers, filter feeders, predators, and scavengers. The late Cambrian world was not being struck by one simple hammer. It was being reorganized by many pressures, some gradual, some abrupt, all translated through living bodies. For animals that had flourished in early and middle Cambrian settings, this reorganization could be severe. A specialized predator depends on the availability of suitable prey. A shelled animal depends on chemistry that permits growth and repair. A burrower depends on sediment conditions and oxygen at the right depth. A sponge community depends on currents and particles suspended in water. A small chordate depends on enough oxygen and food to keep its active body moving. When the environment changes, specialization can become a trap. The same traits that make an animal successful in one setting may limit it in another. A body built for a narrow role can lose its advantage when the role itself fades. This is one reason the Cambrians' most unusual forms feel so fragile in retrospect. They were not poorly made. They were precisely made for worlds that did not last. Their disappearance does not mean they were evolutionary failures. It means that Earth kept changing. Radiodonts, for example, remained important through parts of the Cambrian and beyond in some forms, but their early dominance did not translate into permanent rule over the oceans. Later, marine predators would arise from other lineages, especially as vertebrates developed jaws and fishes became more powerful. Trilobites, by contrast, survived the Cambrian and became one of the great success stories of the Paleozoic, diversifying across ancient seas for hundreds of millions of years before finally vanishing much later. Brachiopods expanded in later Paleozoic oceans. Echinoderms continued to explore plated bodies, stalked forms, and eventually the more familiar shapes of sea stars and urchins. Mollusks persisted and diversified into many modes of life. Chordates, still modest in the Cambrian, carried forward a body plan that would later become central to marine and terrestrial ecosystems. The aftermath of the Cambrian explosion was therefore not a collapse into emptiness. It was a sorting. Some experiments ended, some became foundations. The ocean did not forget the Cambrian, it inherited from it. This inheritance is visible in the major animal body plans that continue after the period closes. The Cambrian established the deep architecture of many groups that still exist arthropods, with jointed limbs and external skeletons, mollusks with soft bodies and often shells, echinoderms with mineral plates and unusual internal systems, chordates with dorsal nerve cords and flexible support, annelid-like worms with segmented or burrowing habits, cnidarians with simple tissues and stinging cells, and sponges filtering water through porous bodies. Not every modern feature was present, and not every early representative fits neatly into living categories, but the broad possibilities had opened. From that point forward, much of animal history would be a story of elaboration, extinction, and return upon themes first made visible in Cambrian seas. The later Paleozoic would bring forests, fishes with jaws, reefs, insects, amphibians, reptiles, and vast ecological transformations on land and in water. Yet beneath those later novelties lay Cambrian foundations: predation, defense, burrowing, vision, shells, segmentation, swimming, and complex food webs. The Cambrian did not create the whole future, but it gave the future a set of durable tools. The losses at the end of the Cambrian also deepen the emotional texture of the period. It is tempting to view the Cambrian explosion as a triumphant rise toward modern life, but deep time resists such a straight path. Many of the creatures that make the Cambrian feel wondrous did not become ancestors of familiar animals. They were branches that opened, flourished briefly, and closed. Their existence matters precisely because it breaks the illusion that evolution moves along a single road. Nature explores widely, and extinction prunes unevenly. Some lineages survive because they are adaptable. Some survive because conditions happen to favour them. Some disappear despite long success. The history of life is not a ladder. It is a branching system under weather, chemistry, chance, and interaction. The late Cambrian declines remind that even a world bursting with innovation remains vulnerable to the planet beneath it. The sea that permits new forms can also remove them. The oxygen that supports active bodies can fall. The shelves that hold shallow communities can drown or drain. The chemistry that builds shells can shift. The predators that drive defences can vanish with the prey that sustained them. In this sense, the Cambrian aftermath is not only an ending to the first great animal radiation, it is the beginning of a pattern that will repeat throughout Earth history. Life diversifies, ecosystems become complex, and then the planet changes the terms. After each disruption, survivors carry forward fragments of what came before. The next world is made from those fragments. The Cambrian survivors would enter the Ordovician, where marine life would diversify again in new ways, building richer ecosystems and more expansive communities. The strangeness of the Cambrian would not be repeated exactly. Later seas would have their own beauty, their own dominant groups, their own experiments. But the memory of the Cambrian remained in their structure. Every shell closing against danger, every animal burrowing into sediment, every predator tracking prey, every swimmer using a flexible body in open water belongs in some distant way to patterns clarified during that ancient explosion. The Cambrian's vanished forms are equally part of the inheritance, even without descendants. Hallucigenia, Opabinia, many radiodonts, armoured worms, and other difficult creatures show how broad the field of possibility once was. They reveal that the present is only one surviving arrangement among many that Earth has tried. Their fossils are not merely curiosities. They are records of evolutionary imagination without intention, forms shaped by real needs in lost habitats, then left behind as conditions moved on. To look back at the Cambrian is therefore to see both abundance and impermanence. The sea fills with eyes, shells, burrows, flaps, spines, plates, and flexible cords. It becomes crowded with bodies that would have seemed impossible in the earlier Ediacaran calm. Then, slowly and unevenly, some of those bodies fade. The radiodont shadow passes into history. The soft experiments become rare memories in stone. The trilobites continue. The caudate thread continues. The shells continue. The burrows continue. The planet does not preserve everything it creates. It preserves enough for the next age to begin. In the last light of the Cambrian, the ocean is no longer innocent, no longer simple, and no longer empty of animal consequence. It has become a living system filled with pursuit, shelter, structure, and loss. The strange beauty of the Cambrian lies not only in the suddenness of its forms, but in the tenderness of their impermanence. For a while, Earth allowed an alien sea to flourish, full of designs that would never be seen again. From that sea, a few enduring patterns moved forward, carrying the deep beginnings of the animal world into the Paleozoic future. The Cambrian Sea recedes into stone, leaving behind the faint memory of bodies that once moved through warm, shallow water under an ancient sun. Its creatures no longer hunt, hide, feed, or drift. Their shells have broken into mineral grains, their soft tissues have vanished, and their strange outlines rest in layers lifted by time into cliffs and mountains. Yet the pattern they began remains. The animal world still carries the old conversation between movement and shelter, hunger and defense, vision and shadow. Every later ocean inherits something from that first crowded age, even when the forms have changed beyond recognition. The Cambrian does not need to be imagined as loud or violent. Across deep time, even its arms' races become quiet. A spine grows through generations. A burrow deepens by small degrees. A swimmer bends away from danger. A shell closes. A predator passes overhead and is gone. These moments gather into history, then settle into silence. What remains is not a single answer to why life became strange and beautiful, but a layered memory of conditions, chances, and living responses. Earth offered space, chemistry, light, oxygen, and uncertainty. Life answered with bodies. Some answers endured, others disappeared after a brief flowering, leaving only their shapes as evidence that nature once explored paths now closed. In that loss there is still a gentle continuity. The vanished forms are not wasted. They belong to the long making of the biosphere, to the slow widening of what animals could be. The Cambrian world fades, but the thread continues into later seas, later shores, and eventually into minds able to look back through rock and recognize an ancient beginning. The strange beauty remains where it has always been, held softly in stone, in living bodies, and in the patient depth of time.